Huh. Oh, hey, Marty. How are you?
Hello.
You're the first one here.
Yeah, I came from anti-de Sitter space.
Oh, yeah? What's going on there?
I quit the theoretical meeting. It was way over my head. In fact, it was light years above my head.
Ha. Wait, what meetup was that?
Michael Sater goes to it also.
Oh, right. Yeah.
Moshe. He's really good, but yeah, it's just so way beyond me. It's just and so abstract theoretical. I mean, it's just nothing in a black hole for me.
Yeah. Someday I'd love to run through some of these black hole calculations myself, but I'm not quite there yet.
You just say.
Oh, looks like Daniel's here. Hello.
Yeah, I just there's someone put up like a factor of 10, series, and it's
Hey,
like we'll never leave our galaxy. We'll never get to the center of our own galaxy, much less any of these other things outside. So,
It's a big place. It's a big world out there.
yeah, I was just looking at the best simulation that's ever been done of atoms and molecules, stuff like that. So they simulated 100,000 atoms.
Whoa.
It took 1 day to simulate 1 nanosecond.
Nice.
Computer that could find.
Well, these days they're getting, better and better, like even just in terms of like classical simulations of really complicated stuff, as long as the problem has some nice, you could use like some kind of tensor network structure. But yeah, it's a snail's pace.
So yeah, we ought to be humble.
For sure.
hi Matthew.
Oh, hello. How are you?
Good. How are you?
Doing pretty good. The weather's nice here.
Oh, okay. It's sunny in California as usual.
It was warm for a bit, like the temperature spiked, and then it like crashed again, and then it was like really windy. And now it feels like spring yet again.
Okay. Did you get to take a look at the podcast that I shared the link to?
Not yet, but I will.
Okay. Actually, these are physics guys. They're talking about physics. I think mostly that they are most likely aiming at their audience to be PhD or masters, people with understanding of physics, because they go over papers. So one thing that you'll notice that he would really like to hear Christopher Fox talking to him about his cubism. So I enjoy the podcast. It's kind of easy. I mean, when I'm driving to listen to things like that.
Yeah. I'll definitely check it out. I need some podcasts.
Yeah. And maybe you can start your own podcast too.
Yeah. I just gotta find my microphone. Lost it somewhere. I've been excited to see that the Quantum Open Source Foundation's been tweeting people's projects like one day at a time.
Oh, they did? Oh, I'm really terrible with Twitter. I'm just sending out when somebody tells me that there's something, and I just reshare it. Or when the page I came across was having that I can tweet, and then I will tweet it.
I'm not such an active Twitter user myself. I mean, I have it. I follow people, like I read it sometimes, but like I made the account back in like 2009 or something, and I just have like a single tweet from then, and I just want to leave it like that. You know, I kind of like the cleanness.
Yeah, well, that's the same. And basically, when I tweet, usually it shows me the Twitter, and then I can say, oh, I have a notification, so I can look what it is. Yeah.
Yeah, it's
and
funny.
Very much the same with Facebook.
Oh, hello, Moshe's here. I guess we should wait like a little bit longer, see if some more people show up. I was excited to see that our old friend Spencer said he'd be here. Haven't seen him.
Is that our Spencer or different Spencer?
Different Spencer.
Okay.
Well, actually, I could, maybe go on like a little tangent while we're waiting. That sort of doesn't like directly relate to what we're going to talk about today, but maybe. I've been sort of like trying to find some papers that make a connection, but you guys know about grid cells?
Nope, that sounds interesting.
Well, that's why we're here, right? To learn.
So grid cells are neurons. This is like a neuroscience thing. And they've been studied for a bunch of years, and they have to do with how, the brain processes like spatial information. And I think someone won a big prize for it in the recent past. Maybe it was a Nobel, I forget. So wait, let me share my screen. Show interesting kind of little video. You'll see the connection to what we're going to talk about today. Let's see, grid cells, mouse. Okay, I think this is it. Well, they must have, they did this. They must have done this a while ago. This looks very black and white. Can you guys see my screen?
Yep.
Cool. So what's going on here is there's a little mouse, okay? And he's in a little box.
Can you increase the size and drop the side things?
Oh,
so
yeah.
like full screen and.
For sure. And
if there's a video, I hope that you selected to optimize for audio.
There's no audio. Okay, so this is a little mouse. He's in a little box, and he's got some kind of thing monitoring a single neuron in his brain. And every time this neuron fires, a little dot is going to appear on the screen, showing where the mouse was when that particular neuron fired. So you see the little guy, he's going around. Okay, and then you start seeing these little spots. So that's where he was when this neuron fired. And, at first they look kind of random. But as they accumulate, maybe you'll start to see a pattern.
Is that somebody's foot I see to the right side?
Sorry, say that again.
Is that somebody's foot?
Yeah, it does. Yeah, it definitely is. Yeah, it looks like a lady's foot. It just looks like she's wearing a
Well,
dress.
that grid must be real big, or maybe it's real close to the camera.
Well, let's focus on the foot now. And I think that they have actually skirt around this because they are filming it, so this is dark.
Yeah,
So
yeah,
the feet, they have actually pants, and it could be a man too.
could be. Yeah, true. So,
Oh,
okay,
look at those patterns.
yeah, so you see that there's like a sort of a pattern there. Let me try to find another one that will make the pattern even more clear. There's several of these videos. No, that's not a good one. Well, oh, maybe this one's good. I'm just gonna take off the sound. Yeah, so okay, so what they found is that these neurons will fire the pattern. It actually makes a hexagonal grid. So it's as if space has been sort of tiled with a bunch of hexagons. And whenever the mouse is like at one of the vertices of the hexagons, this one particular neuron fires. Then so that's what's known as a grid cell. So a grid cell has this property.
Mhm.
Now, there's like a bunch of grid cells, and each one is sort of sensitive to a different hexagonal grid. So you imagine like you take a hexagonal grid and you could like rotate it. You could, kind of scale it up and down, or you could sort of like phase it. And each grid cell is tied to like a particular, hexagonal lattice. And the mouse kind of, it's not so much, as I understand it, that the mouse is like sort of synthesizing like the sensory information and then like making the neuron fire, so much as the mouse knows how it's moving. Okay. So you have all these different lattices, each one's associated with the grid cell. And then all these grid cells kind of feed into what are known as place cells that kind of like synthesize that information into like a neuron that fires like when you're in a particular place. And I just find this interesting, because we think about space often. I mean, unless, it's like in a general relativity kind of context. I mean, space, it's like 3D, get some XYZ coordinates. Well, you wonder like, well, how does the brain actually process, spatial information, like how we know where we are, how we map out like the spaces that we move through. And, it's actually this sort of more complicated kind of interesting thing. It's as if there's all these randomly generated sort of hexagonal lattices, okay, that are all like overlaid, and each neuron is tied to one of them and they're firing, and then all this information is sort of synthesized. What we're going to talk about today is frame theory, and one particular kind of frame that's important for various reasons are equiangular frames. So they consist of vectors that all make equal angles with each other. And in 2 dimensions, the famous example of a hexagonal frame is exactly the diagonals of a hexagon. And, this is sometimes called the Mercedes-Benz frame, which explains the image for this meetup, because just sort of look at the unique sort of lines here, half of them, they make that shape.
What's wrong with the hippie peace sign?
True. Well, yeah, I was thinking about that too. But I guess that has like another. You're right. That would work too, and probably better because less association with fossil fuels.
Matt, are you now wealthy enough to afford a Mercedes, or
Yeah.
like the previous gentleman asked, is that a peace sign?
Yeah. Well, I should get a Mercedes and then replace the logo with the peace sign.
Well, if they don't catch you, you can get the Mercedes symbol passing by a Mercedes, but it's apparently very difficult to pull it out.
So where's it? Did you build this notebook, or did you get this somewhere?
Yeah, I built this. Yeah, and as I mentioned in my response to Michael's comment, there's some, if you want some more official sort of references, these papers are here. I mean, this book here, An Introduction to Type Frames, is sort of like the Bible. It's like 600 pages of everything you ever want to know about frames.
Is that on Amazon or is that just somewhere out on the internet?
All of these that I linked here are
Hold on, let me get it.
freely available. I mean, I don't know how legally, but though actually, well, this is provided by the author on his university website. Waldron posted this, so it's okay.
But go back to those links. I want to take a snapshot real quick.
Oh yeah. Well, I should mention here. I'll send actually a link to this. You can read it. You can just get the links.
Can I ask a question, Matt?
Sure.
Before, on Hey Red Hat, you, at least last week, you posted a couple of references. Let me quote the one by Flaminia, Giacomini, Ruiz, and
Oh yeah.
Quantum Mechanics and the Covariance of Physical Laws in Quantum Reference Frames. They state the state of a physical system has no absolute meaning, but is only defined relative to the observer's reference frame in the laboratory. Isn't this ass backwards? Isn't it the other way around? That the reference frame is relative to the state. The state is absolute. State doesn't change.
Well,
Maybe just a minor point, but that's what I read, to prepare myself for this meetup.
so yeah, well, so that was, we won't really be talking about that exactly this time around. In the quantum reference frame community, that is how they, they don't look at quantum states as being objective, whatever descriptions, given once and for all for everybody, but quantum states are relative to, your, observer position, however you want to define that, and so they, in that paper work out, what are these sort of reference frame transformations, and, their innovation was to sort of come up with an idea of like a quantum reference frame shift. So, if this one system's like in an entangled superposition, but you want to use it as a reference frame, how can you do that?
Of course, we anti-Copenhaganists object to that. We believe that states of physical systems are absolute, and the reference frame is what's relative.
Well, okay. All right. Well, I mean, so there's, one camp of people who, as you say, as you yourself do, reify or objectify the quantum state as.
Wait a minute, reify? What? I flunked out of third grade. What does reify mean?
Well, translation means to thingify, right? To treat the quantum.
Oh, okay.
Okay. So then you have more people in like the reference frame stuff, or like Carlo Rovelli's sort of like relational quantum mechanics. There's like different, so there the idea is sort of like the quantum state is, always like a relative quantity. Okay. Now, if anything, I mean, like what we're gonna talk about today is sort of, at least at the end, sort of inflected by cubism, which goes even further, right? Where they just think of quantum states as essentially like probability distributions. So they have a very epistemic take on a quantum state. So that's even a step beyond the relational quantum mechanics stuff.
I have a question here, since basically my cubism touch is coming from the podcast I was listening the other day, and if you had a quick passing by, actually I got the feeling that the point of the cubism is that the state is actually reflecting on our understanding of nature, of process. And like Michael was saying, originally in classical physics, we are starting with objective states, so that things exist without us influencing them. And it makes sense in classical terms. when we don't disturb the system when we're observing it. But in quantum system, it is not anymore the case, but still we are trying to kind of put some objectivism there, and that's what creates the problems. And my understanding was that in cubism, they say, well, the state of the wave function, basically the system in quantum mechanics reflects our understanding, because but it didn't seem to me that it goes into further saying, well, maybe there's objective state, but we don't capture the whole thing. We're just capturing it on one little window on our side, which makes more sense to me. But now you're saying it's you didn't touch anything on this direction. You're saying just distribution, but that's basically distribution is for almost everything. Distribution is the key thing for any interpretation. The question is what distribution means.
Yeah. So I mean, even quantum mechanics aside, just thinking about classical probability theory, there's the argument between the frequentists and the Bayesians or whatever. And one camp says that the goal of probability theory is to update your probability assignments until they reflect the objective probabilities that nature has lying in wait for you. And then there's the Bayesian approach, which says no, things don't have objective probabilities. Rather, Bayesian updating, et cetera, is like a way of different people converging on a probability distribution to the extent that they regard different experiments as essentially permutable, or the substitutable for each other. They sort of my point is that even for normal probability, there's a sort of subjectivist interpretation and an objectivist interpretation. I mean, cubists, as they will always eager to tell you, are not solipsists. They are like, quantum systems are real, okay? But they are not reducible to quantum states. Quantum states are our tool for trying to understand them.
So then, Matt, cubism is still a probabilistic theory like Copenhagen. So what you're saying is that your belief is that there is no objective reality in the universe. Am I correct?
Well, I mean, define objective, it's like.
Well, an actual existing singular state for a system.
Michael, let me try to define objective. And what Matthew said about the probability interpretation, this sounds like interpretation on one side where you're really classical observer that does not influence the system, therefore, and you're kind of godlike observer who have all the power to get all the information needed to assign this. Ideally, this is almost a closed system that you're observing, and therefore, every observer should get the same probabilities. But in reality, systems are not really closed, and we are not godlike observers. So we do influence the system when we do the observations. So Bayesian, then it makes sense in practical sense because you want to update as you go. Now, to me, the objective now is coming in the following. It's just like active and passive frames. The objective would be something that's given enough observations, different observers, and enough data kind of processing. Eventually, we will all figure out how to translate observation in one observer to something to be consistent with another observer. And as a result, in this class of equivalences, this would be the objective reality, because any other observer would be a member of this class. And if it is not, it will be just kind of incorporated down the road. So that, to me, that's the objective reality.
Yeah.
Well, of course, objective reality exists regardless of the observer's existence. And of course, an observer in a quantum system affects the reality. So what are we talking about?
Well, there's the other thing that people are pushing, that basically reality is created by us asking questions about it and trying to receive answers. So probably I can pass to two more kind of links in the chat later. That's Weaver's idea for its from bits, which he's building like three postulates and 5 conditions. And this is kind of interesting to listen to the podcast. So in this respect, some people who say that every observation, every act of interaction changes the reality, it's correct, but it doesn't change the overall reality. And I think one piece that is missing in all these things is really that at some level, these changes are irrelevant to the global picture. And in this respect, that's why it looks like there is no objective reality, because the result of different observations may result in kind of different things. But in the global picture, I mean, what effects does it matter when I do measurement on a subatomic particle? I mean, it doesn't change my table. That's, I mean, I'm doing the experiments and I mean all the other stuff around me in my everyday life, right? So
Yeah,
I think that's one thing that is missing in the overall measurement process.
so I think we should move on to the notebook and then circle back around to these, more metaphysical issues towards the end, where they'll come up, I think, somewhat more naturally.
Yeah, I agree.
So, all right, let's do this. Okay, so, everyone knows about orthonormal bases. We know and love them. Thanks, Descartes, x-axis, y-axis, right angles. Great. And they're so useful that we, often don't think that there's just more flexible ways of, using coordinates. And one of these is a so-called frame or over-complete basis. So, if you relax the condition of like orthogonality, of course, you can have just a merely linearly independent basis. But you can also, just use coordinates where the vectors aren't even linearly independent. And that's what the overcomplete part means. So there's actually redundancy, okay? Redundancy in the coordinate system. So for a frame, you can have as many elements as you like. I mean, as long as it's greater than the dimensionality. And in fact, with probability 1, like any randomly chosen set of vectors will form a frame. So for example, let's just work with D equals to real vector space. Okay, simplest, why not a frame made out of 5 vectors? Here they are. So, these are the columns of this little rectangular matrix, just randomly generated. We can form the so-called Gram matrix, or the matrix of inner products, like so. And so, one condition for everything being kosher, frame-wise, is that this Gram matrix ought to be rank D, where D is the dimension. And as you see, look at its singular values, it's got 2, the rest are 0. So it's rank 2.
So is that the product of the different vectors in the original matrix, or?
Yes, right. So R here is this sort of fat matrix, and then R transpose is the tall matrix, and you multiply them together, and you get this square matrix. Yes, this is R. This is the matrix of the vectors, and this is transpose. We can also go the other way around, multiply R times R transpose. And if here, we got a 5 by 5 matrix, here we get a 2 by 2 matrix. And we'll have a frame if this guy has non-zero determinant. In other words, this guy has to be full rank. And what that means is that the rows of this matrix have to be linearly independent. So normally in a basis, we would think about like the columns would be linearly independent, but here actually the condition is that the rows are. So we can check, is this determinant non-zero? And behold, it is. One of the technical definitions of a frame is a set of vectors V for which there's constants A and B greater than 0, such that this little inequality is satisfied. And A and B are called frame bounds, but we won't actually be using this definition really today. But the conditions I already mentioned, basically have this as a consequence. But for completeness, I put it here. So let's see how we actually use them. So suppose we have a point in 2D. There we go. We can expand it in our frame vectors by just taking the inner product with each of the frame vectors. And we get 5 coordinates. There they are. For this reason, this matrix, R transpose, is often called the analysis operator. So taking our point, kind of analyzing it into components. Okay, how do we recover our original point? This is, what sort of makes it different from, your usual orthonormal bases, where, well, you'll see. What you need to do is use the dual frame. So this even comes up, like in quantum mechanics, we're used to being like, well, you have a bra and a ket, and the bra is just, the conjugate transpose of the ket, okay? Well, if you were working with linearly, just merely linearly independent vectors, then there wouldn't be such a simple relationship where one is just, conjugated column vector, one's just a row vector, whatever. So, you need to form, the vectors would be different from their duals. So this comes up here as well. So to get the dual frame, we take the pseudo-inverse of R. And then the inner products with the frame vectors turn out to be the weights on the dual basis vectors, which via summation recover the original point. So we take the pseudo-inverse of D and we get this little guy. And then if we multiply these little coordinates here by each of the dual vectors and then add them up, we recover our original point.
Can you quickly explain what do you mean by pseudo-inverse?
What is even the definite, how do you even, I forget how to calculate a pseudo-inverse.
Do you mean it's like left and right inverse?
The Moore Penrose inverse.
It's the matrix such that if you multiply by the original matrix, but you basically get basically the least squared reconstruction of the diagonal.
Yeah.
The identity matrix or
Yeah.
something.
Yeah.
But then
It's basically the best approximation you can get to an inverse matrix that an inverse can't have. For a matrix that can't have a matrix.
Is it related in any way to a left and right? For example, if you don't have an n by n matrix, you might try to talk about left and right inverse, a way that when you multiply on left, you get one quadratic matrix that's the identity matrix. And when you do it on the other side, you get another identity matrix in a different space.
Yeah.
Well, yes. So like in this case,
Yeah. The way it's normally calculated is you multiply the matrix by its transpose, invert that, and then multiply it, I forget it, by the original or by the transpose again. And then if you kind of do some little sort of like back of the napkin calculations, you'll show that at least you can show quite easily that gives you an inverse, at least in the case when there is an inverse. And then.
Thanks.
Okay, I see. Yeah, thanks.
So as I say here, we have our coordinates given by the inner products with the frame vectors, and they weight the dual vectors, and then we can recover our original point. We can also think about this as just multiplying the coordinate vector by D transpose, and D transpose is therefore called the synthesis operator. So, R transpose analyzes the vector into components, and then the synthesis operator puts them back together again.
Could you full screen your browser by any chance?
Sorry? Oh, full screen.
Full screen your browser, yeah.
Yeah, for sure. Okay. And because we did the pseudo-inverse thing, RT times DT is just the identity. And that's why it works, right? Because, if we just analyze C with RT and then multiply it by DT, that'll, undo it and we get back our original points. We could go the other way around. We could expand in the dual basis, and those would give us the coordinates that would weight the original frame vectors. Another way of thinking about this recovery procedure, without invoking the dual basis explicitly, is instead to take the pseudo-inverse of the Graham matrix itself. So here we get G inverse. If we then have our frame coordinates here, and then we act with G inverse, we'll end up with the coordinates in the dual basis. If you look up here, here's the coordinates in the dual basis from before, and that gives us this. So that, we can sort of avoid working with the dual basis explicitly by just multiplying our coordinates by G inverse, and then those will give us the coordinates that weight the original frame vectors, and then we get back our original point. So, that's basically a frame. Okay, as you see, it's not that complicated, okay? It's just simple, quite sort of beautiful, just more flexible idea of a coordinate system. There's different kinds of frames, okay? That's really the art, right? There's different kinds of frames that have different properties that, you might be interested in. I mean, I should say, I don't know all that much at the moment about the history of frame theory. But I understand, it had its origins, in signal processing, like in the 50s. And, okay, so, everyone knows about the Fourier transform, okay? You can have a signal, you can express it in the time domain, it's going along. Take the Fourier transform and express it in the frequency domain. And of course, there's, a sort of complementarity between the two. What you might wonder is, like, there's something in between these two representations where you have, like, both, time information and frequency information. And, in fact, if you're a musician, this is very intuitive, because musical notation itself is an example of this, right? You have, like, your staff, and you have your notes, and they proceed in time, okay, time information. But then you can stack the notes on top of each other and make chords. So actually, musical notation is kind of like an in-the-middle thing. It was the attempt to kind of understand, like, that sort of thing that led to, the early frame theory work. And, there's a connection to, like, wavelets and coherent states and whatever, okay? But, we're just going to be considering finite frames, okay? Just finite dimensional, finite numbers of vectors and stuff. But, people work in the infinite dimensional case all the time, I should just mention. So, okay, so one useful kind of frame, as we'll see, is a so-called type frame. So we can easily get one just randomly via a generalization of the polar decomposition for rectangular matrices. So we can generate, a random R like we did before, a little, 2 by whatever 5 matrix, and then decompose it using this generalization of polar decomposition for rectangular matrices into a rectangular matrix, which is like a unitary in the sense that its rows are orthogonal, and a Hermitian matrix, H. And then we just throw away the Hermitian part. The point is that we want a rectangular matrix whose rows aren't just linearly independent, but are in fact orthogonal. And that is what defines a type frame. So here we go, we get one. We can look at its Graham matrix, but then we can look at R times RT and notice it's the identity. Okay, so that happens because it's a tight frame. Before, we just had like a random old frame. That little matrix was not the identity. It was full rank, but it was not the identity. Tight frames is going to be the identity. And what that means is that in this case, the frame is the same as its dual. In other words, the analysis operator is R transpose, and the synthesis operator is just R. So we can have a point, we can analyze it, and we can synthesize it, and we get it back. More generally, any frame for which R times RT is proportional to the identity is a tight frame. So notice, proportional to the identity. Doesn't have to be equal to the identity, it just has to be equal to the identity times something. And in that case, in general, the dual frame will be proportional to the original frame. And in terms of the frame bounds from before, that little inequality, tight frame means that A equals B. And in fact, when A equals B equals 1, it's called a Parseval frame, whatever. Just throwing it out there.
Matt, can I ask a question? Is this the same Gram as in Gram-Schmidt decomposition of the
I don't
matrix?
know, but I would bet on it. Yeah.
Because I've usually seen his name spelled with 2 M's, but you know, it could be somebody else. Just curious.
Maybe it's the Gram-Stain guy.
Sorry?
Maybe it's the Gram-Stain guy.
Okay.
Biology, the gram-positive and gram-negative bacteria.
Right.
Yeah, I don't know who Graham was, but sometimes it's also, you know, if you're looking it up, sometimes called the Gramian, instead of just the Gram matrix.
Of course, there's a much more advanced theory, the kilogram theory. Never mind.
So, as I said, the Gram matrix of the general frame has got to be rank D. In the case of a tight frame, Gram matrix is in fact a rank D projector. So it's going to have, you know, all but D eigenvalues are going to be 0, and those that are non-zero are 1. Another useful kind of frame is a so-called unit norm type frame. In other words, this vector has, all the vectors have unit norm, okay? You can easily get one, and this is actually kind of surprising that this works, by alternating between tightening and normalizing your vectors until you're close enough. So in other words, this code goes in, generates a random frame, gets the tight frame, normalizes vectors, tightens it again, normalizes it, tightens it, until, you know, up to numerical precision, the vectors are in fact tight and unit norm. So there you go, boom. And you look at the Gram matrix and, you know, there you go. One's along the diagonal, unit norm. And we can check it out. And in fact, there we go. R times R transpose is proportional to the identity. In fact, it's proportional to N over D times the identity. So, you know, we can take our point, we can analyze it, and then we can synthesize it. And you notice we just sort of multiplied R by D over N. We could have, you know, if you wanted, you could absorb this into the definition of R and R transpose, right? You could just sort of multiply each of these by the square root thereof, you know. Next, we have the equiangular frames, okay? Call back to the thing with the mouse. Everyone loves equiangular frames. The vectors form equal angles with each other. Well, the absolute values of the inner products, as you'll see. And, you know, it's known that, like, one of the reasons these are cool is that they're, like, very resilient. In other words, you know, with the normal, you know, Cartesian frame, it's like you're thinking about it's great because it's very minimal. You know, it's just like you're in 2 dimensions, so you have like 2 numbers to describe your point, you know, obviously. But, you know, you're thinking about like, well, what if there's a chance you could lose one of your components? Well, your Cartesian axes are not gonna, you're gonna lose, a heck of a lot of information. You lose like, what's going on in the y direction. But like if you have an equiangular frame, it's particularly resilient if you lose some of the components. And so it makes sense, that like biological systems, might want to use these. But interestingly, and we'll circle back around to this point, there are like geometrical restrictions on the maximum number of equiangular lines you can have in a given dimension. So for example, in 2 dimensions, there's like a maximum of 3 equiangular lines. And so we can easily construct the vectors corresponding to them, like so, just sort of get, some roots of unity, whatever. And as I say, this corresponds to these diagonal lines, diagonals of a hexagon, or the Mercedes-Benz symbol.
So what stops you having more? I mean, presumably you can, you can divide a circle into any n simply by solving any polynomial, right? Any nth root of unity. Is it that, I mean, I don't see anywhere a requirement that they need to form like a regular tiling pattern or anything like that, because that's presumably where the restriction comes from.
Right, well, because like if you had more, then, it's like you could divide up the circle, but then like this one and like this one would have different angles than like this one and this one. As far as like the proof, it's interesting, there's like bounds on the number of equiangular lines that people have proven over the years in different dimensions. And the proofs are often kind of tricky, involving geometrical arguments that are somewhat beyond me. So like why, I can't answer necessarily off the top of my head. Like, is there a particular restriction in a given dimension? Like why that exactly is. So you can see here, looking at the Gram matrix, indeed the inner products here are all, negative a half. And it's tight. There you go. In 3 dimensions, there's an equiangular frame. Oh, and I should say too, I mean, this is not uniquely defined, right? Because like I could just like rotate these and it would also be an equiangular frame. But notice that would have like the same Gram matrix, or maybe like a permuted version of the Gram matrix. So, in fact, this is not unique. There's just like a whole class of them, obviously, because you could just like rotate them. So in 3 dimensions, the icosahedron provides us with an equiangular frame. So the icosahedron has 20 faces, 12 vertices. And if you connect up the diagonals, there's going to be 6 of them. And those 6 directions provide your frame vectors. And so you can generate those. It's kind of cute. Here's a function that takes a vector and returns all the shifted versions of it. So like 1, 2, 3, 3, 1, 2, 2, 3, 1. And then you can generate the vertices of icosahedron by starting off with the golden ratio. And then take these 4 vectors and generate all the circular shifts of them. And that will give you 20 vertices. And then we throw out the antipodal ones and we get the 6 vectors, we normalize them. So here's our icosahedron frame. And this is why I mentioned like the absolute values of the inner products, because if you look at this, they all the absolute values are the same, but the sign structure is, important. Okay, so like some of these are positive, some of these are negative. And, that actually, you follow that thread out and it turns out to be a whole interesting aspect of this problem, the sign structure. And as you can see, it's a tight frame. So yeah, let's visualize this for a second. Have a little visualizer. 2D. Brain viz. All right, so hopefully this will work. Okay, you guys can all see this? Maybe. So here we have a point in 2D. Here we have our lovely Cartesian axes. And we can look at the projections onto those axes. Okay. We can also look at, our equiangular frame. And so we can project onto those guys. We can also look at the dual frame, project onto those. In this case, it's a tight frame. So as you can see, the frame is proportional to its dual. We can then look at, okay, let's look at here's the frame vectors. We can then, right, so if you recall, we take our coordinates, multiply it by, say, G inverse, and then those provide the weights on the original frame vectors. So that's what you see here. You take those components and, I've sort of represented them here with these purple dots. And so each of these, as you see, is like an instruction. Go a certain amount in this direction, go a certain amount in this direction. And then you see that recovers the original point. You can do the same thing in reverse, right? Like take the components, the inner products with the frame vectors give you the weights on the dual vectors. And so, in this case, it's about the same because, of course, the frame is proportional to its dual because it's a tight frame. Well, I'll show you the more interesting. It'll be more interesting, when we have like a non-equiangular one. One kind of cool thing, though, I'll just show you here, though, is it's useful in this case where we're just working in 2 dimensions. What you see here is I take the dual frame, okay, and then I look at its columns, okay. So there's, in this case, 3 dual vectors, okay, in 2 dimensions. So then I look at the columns, it's 2 vectors in 3 dimensions, okay. So those are those 2 axes here. So you see, those are actually like lines in 3D. I can then take the frame coordinates, okay? So this 2D point expanded in the frame vectors. I get 3 coordinates. I can then just pretend those are that's just like a point in 3D. And that's that green dot there. Now, what's interesting is if you look at the projection of that green dot onto these 2 lines in 3D, it gives you the same thing as if you just take the original 2D coordinates and weight these 2 vectors. So it's like if I have my XY coordinates and I say, okay, X means go this much in this direction and Y means go this much in this direction, I actually recover this point. Just to give like a sort of an intuition, like in higher dimensions, like you can't do this visualization. You see the whole, this gets at the issue of normally, your basis vectors have to be orthogonal or linearly independent or whatever. The whole trick of a frame is that, you have that rectangular matrix, and instead of the vectors themselves being linearly independent, it's like the rows that are linearly independent. So let's look at just another kind of frame. So let's look at a random, well, it's like a random frame. 2 dimensions, and yeah, let's do 3 again. So, okay, we have our Cartesian. Okay, here's, you know, the frame vectors. They're just completely weird looking, right? In general, the dual is just going to be some other weird thing. And we can look at the, oh, here we go. These are the, you know, the inner products with the frame vectors gives us how far to go in each of the dual directions to recover that point. And similarly, the dual components give us how far to go in each of the directions of the frame vectors to recover the original point. And beep, beep, beep. Oh boy. Just, you know, can't remember what any of these keys do. And then we can look at our weird 3D thing too. So now these are, you know, also weird looking.
So how are you getting it into the 3D? I mean, how are you constructing the extra dimension?
Right. So, say you take the, here's the dual basis. So here, you know, the rows, the two-dimensional rows are the dual vectors. But we could also interpret this as 2 points in 3D. So you have this 3D,
Okay, I see.
this 3D coordinate, and they provide the
Yeah.
3D. And then the point is actually just this number, which is the frame components, just interpreted as a 3D point.
Okay. Yes.
Okay, so, you know, just to give you some intuition, you know, there's a little bit of sleight of hand here because, you know, when we expand in the frame vectors or the dual vectors, we're taking the inner products, but what I showed you there are like the literal like orthogonal projections onto those lines. And so, you know, you actually have to divide those numbers by the norm squared of the frame.
Well, the reason I ask, because in the usual metrics, usually metrics is viewed as isomorphism between the space and its dual. And basically when you have, I mean, non-degenerate, it's, I mean, they have the same dimensions. In this case, they have different dimensions, the two spaces. So the dual could be different. And
although, I mean, they have the same, I mean, in both cases, like strictly speaking, it's like, okay, you have like 3 frame vectors and 3 dual vectors. But then there's this, you know, part of like the geometry of what's going on is you can also think about the dual frame as being these like these 2 3D guys.
right, but what I was saying is that naturally, I mean, the most convenient one is when the isomorphism is very simple. So it's like the Euclidean space, and it gives you the Cartesian coordinates. And then basically when you do calculations, you don't think, am I using the dual vector or the vector when I'm doing a dot product and all this stuff.
Precisely, yeah. So, I mean, that's why people like the tight frames. So, right, here, let's do like 5 vectors. Right, the tight frames are those for which the dual vectors and the frame vectors are just proportional to each other. So, you know, here's like a frame. And then you see the dual frame, they're all pointing in the same direction, but they're just like rescaled.
Yeah. Well, the reason I was asking is that there's the other thing is when you have difference in the size, for example, in string theory and other elements, I mean, you have a target space, which would have some background metric, and then you embed the actual space or the system that you will be considering in a smaller space, for example, a string embedded in 3-dimensional space. And when you have this kind of spring embedded in 4-dimensional space. The interesting thing is that when this embedding is kind of inducing also a metric in the smaller space, in the embedded space. And of course, the embedding is the question is how are this embedding performed?
Well, yeah,
And,
I think here
yeah.
it's almost like the other way around. It's like you have a smaller space, and then you're like embedding it in like a redundant way in a larger space, and then like recovering, you know, the original thing back in the smaller space.
Right. So in a sense, this is important from, and I think probably it will come again and again in information theory, where you have a set of parameters that should be the maximally independent vectors, but then you can have overcompletion of your system with the data points that would have much more, so that you have to try to figure out what is really the actual physical space and what is the extra space.
Right. Yeah, for sure. Okay, so now we turn to a related topic, as you'll see. So, okay, we're still working in 2 dimensions. We have our, you know, our 2D frames, can have our, you know, whatever random frames, our type frames or unit norm type frames. We could have, you know, as we've seen, you know, 5 frame vectors, whatever. We saw in the equiangular case, you know, we could have a maximum of like 3 equiangular lines. Well, 3 is an interesting number in this case because 3 is also the dimension of the space of 2 by 2 symmetric matrices. In general, in D dimensions, the space of symmetric matrices is D times D plus 1 over 2 dimensions. And we might be interested in this if we wanted to do real vector space quantum mechanics. So in this case, pure states are given by just 2-dimensional vectors. You know, this is like a simplification of quantum mechanics, obviously. 2D vectors such that x squared plus y squared equals 1. Okay, this means they're points on a circle. Or, you know, we could also think about that as a rank 1 density matrix. In other words, a density matrix that can be written as like an outer product of like one of these pure state vectors. And as I'm sure y'all know, a density matrix might in general be higher rank, a statistical mixture. And in general, any, you know, symmetric positive semi-definite matrix with unit trace will do. Now here's the big reveal. Here's the connection. Turns out type frames are just rank 1 positive operator value measures in disguise. Okay, so, you know, we talked about POVMs or whatever a couple weeks ago back in the day, and now it comes back. Okay, so recall that a POVM is a set of positive semi-definite matrices that sum to the identity. Okay, so you have them. They're called elements of the POVM. Here, EI, they sum to the identity. Each one of these elements represents an outcome to a generalized quantum measurement that concretely involves entangling your quantum system with some apparatus such that the dimensionality of the apparatus is equal to the number of the POVM elements. So, you know, for example, like for a qubit, okay, 2 dimensions, this is in the complex case, 2 dimensions, you could have, say, a POVM with 4 elements. As you'll see, that's the one you want. So, you know, you have your 2-dimensional system, and then your apparatus would be 4 dimensions. Or in this case, we were just considering in real vector space, you know, you might have 2-dimensional system and then a 3-dimensional apparatus. And what this experiment consists in is taking your system and your apparatus and entangling them in a special way, in a way that can be derived from the POVM elements. I talked about that before. We won't go into the details of that here. And then ultimately doing a standard measurement or von Neumann measurement, a projective measurement on the on your apparatus, on your reference system. So in the case specifically of a rank 1 problem, the outcome states are correspond to the normalized problem elements. So in other words, you'd have your system and then your apparatus, and you entangle them. And then the idea is like, if you say get the first outcome on your apparatus, then your quantum system is steered to the density matrix that's like the normalized version of the first problem element. If you get the second outcome of your apparatus, then the outcome is the normalized version of one of these matrices EI. So in general, a problem can have like any number of elements. Dimensionality of the underlying Hilbert space be damned. You could have 2 elements, 3 elements, whatever. Doesn't matter. They just have to sum to the identity. But we're going to be interested in so-called informationally complete problems. And the point of these is that they have at least as many elements as the dimensions of the relevant operator space. So, I mean, they could have more, but we'll be interested in these like minimally informationally complete problems. And what that means is that they span the space of density matrices. That's why.
Can you increase again the size of the screen?
Yeah. Oh, yeah, but I forgot. Thank you. So for example, in real quantum mechanics, as I said, the space of density matrices is d times d plus 1 over 2 dimensional, where d is the dimension of the Hilbert space. And for d equals 2, that's 3. In normal, complex quantum mechanics, the density matrices are like Hermitian, et cetera, and they'll have d squared parameters. So why do we care? It's like if we have enough elements in our problem to span the operator space, then the vector of probabilities for each outcome, like the probabilities that you get each of the outcomes of this experiment, suffice to completely determine the quantum state. And so this allows you to do quantum tomography in a very elegant way, in a way that treats pure states and mixed states on a completely equal footing, and which involves repeating a single measurement over and over and over again, right? Like normally you'd have to do complementary measurements. Like you have a qubit, you want to reconstruct its state, got to measure in the X direction, Y direction, Z direction on a bunch of copies and put it all together. Here, you just repeat the same one measurement over and over again. So if we have a tight frame, we can upgrade it into a rank 1 positive operator value measure by just taking the outer products of the vectors with themselves. This, as I say, turns out tight frames are just rank 1 problems in disguise. And by the way, it's like your problem elements don't have to be rank 1, but we'll just be considering that kind here. And indeed, if the problem elements are rank 1, then we can write this condition that they sum to the identity as just this, and that ends up being just the same as R times R transpose. Boom, boom. So here we generated a random tight frame, and here we upgraded it into a problem by just taking the outer products of the vectors, and they sum to the identity. Behold. So then, okay, so let's do this. Let's see how it works. So let's generate a random density matrix. Again, this is all in like real quantum mechanics. By the way, if you don't know how to generate a random density matrix, here's a nice way of doing it. Given a dimension d and a parameter n, which is going to control the amount of mixedness, then you generate like a rectangular d by n matrix, multiply it by its transpose, so that you know, the n part collapses away and you just get a d by d thing back, and then divide it by its trace. And if n was 1, you would get, you know, rank 1 density matrices. And the higher n is, the more mixed it's going to be. So, okay, so we have some random density matrix rho. We can, just as we, you know, expanded in frame vectors when we had our 2D point, we now have this 2 by 2 density matrix. We can expand it in problem elements. And in order to do that, we simply take the trace of each of the problem elements multiplied by rho. And we get these 3 numbers. And in fact, these 3 numbers sum to 1. And in fact, these 3 numbers are the probabilities for those outcomes. So, you know, the image to have in your mind, again, is to have, you have your quantum system, then you have your apparatus. They're entangled in such a way that then, you know, your 3-dimensional apparatus, if you look at the probabilities for, you know, a measurement in the standard basis, though you're going to get those 3 probabilities. And then when you actually like do it and you get one outcome or another, if you got this first outcome, then the system would end up being in a state, you know, proportional to that first problem element. If you get the second outcome, then you get a state proportional to the second. I say proportional because, you know, it's going to have to be a density matrix. Its trace is going to have to be 1. These have all been squished basically so that they sum to the identity. And so, you know, you just divide out by the trace, you just get the projector version of it. Okay, so back when we were just talking about frames, we had a point, we expanded in the frame vectors, but then we wanted to recover, we analyzed our vector, but then we wanted to synthesize our vector. We wanted to recover that original point. And so we used the dual basis. Okay, so but like, how do we do that here? Now we're talking about operators and stuff. So we need the dual basis, but like, what does that mean here? So what you do, one way of doing it, is, okay, so first of all, like notationally, if I have a matrix A, I'm going to denote by like this little guy, the vectorized version of that matrix, right? So you just take like the rows of the matrix or whatever, and you just sort of, you know, put them all in a row. Now you can think about another way, it's sort of fancy, not that fancy, but you know, one way of thinking about this, which those of you who recall some of our string diagram adventures will know well and love, is you can think about this like vectorization of a matrix as simply double your Hilbert space, get the maximally entangled state, the cup state, okay? So the sum over just, you know, all the ith basis states twice, and then act with this matrix A on the left. And then the resulting state will just be the vectorized version of that matrix. So then you form the so-called frame operator. So you take all of your problem elements, you vectorize them, take the outer products with themselves and add them up. And that's the frame operator. Now in this case, because our problem is rank 1, this actually turns out to just be equivalent to sum over the tensor product of the problem elements. And the proof is kind of cute that this is true. So we have, you know, by this definition that the vectorized version is just EI acting on the left on the maximally entangled state, but EI is rank 1. So we can write it like that, where like those are the frame vectors. And then we can just like bring that inside the sum, you know, have this guy act on this first guy here. And then we can bring this part out of the summation, but then this is just a sum over the jth basis states, each one inner product with R. Well, that's just R. And so we get the tensor product of R with itself. And so then when we look at this, that's just, you know, R tensor R, and then the bra version R tensor R. And that ultimately we can kind of switch around the outer product and the tensor product to get this. And that just turns out to be EI tensor EI, it's all summed over. Okay, so finally, you take the pseudo-inverse of F, all right? So you get to your matrix F, your frame operator, and you try to invert it. And then if you act with F inverse on these vectorized Pavum elements, you'll get the vectorized dual Pavum elements. And then you just reshape them into a matrix. And then you have your duals. Okay, so you take all your Pavum elements. In this case, we can just tensor them together, each one, add them up, take the inverse, and then go over each of the elements, reshape it into a vector, act with F inverse, and then reshape it into a matrix. And we get our dual elements. So if we have our row, we already up here got the probabilities by taking the, getting the probabilities on each of the Pavum elements. And then we use those to weight the dual elements. And we add, multiply each probability by the dual, add them up, and we recover our density matrix. We could have gone the other way around, just as before. We could have expanded in the dual elements, gotten these numbers, and then those numbers would weight the Pavum elements, add them up, and we recover our row. Now, one thing that's worth noting is that these, what's the deal with these dual basis elements? You might wonder, do those form a Pavum? And it's like, they don't. And in fact, their elements must be indefinite matrices. Like a Pavum, recall, has to consist of positive semi-definite matrices. But the dual elements cannot be positive semi-definite. So they're not, the dual is not a Pavum. So before, we had our frame, we had our dual frame, but then there was also this trick of taking the Gram matrix and inverting it and using that instead of explicitly invoking the dual basis. And so we can play a similar trick here. But instead of taking the inverse of the Gram matrix, we're going to take the Gram matrix is the Gram matrix of the original frame vectors. We're going to take the Hadamard squared of it, so just the element-wise squared, and then inverting that. So we take rho, we have our probabilities, we form the Gram matrix of our frame, we element-wise square it, take the inverse, and then when we act with G squared inverse on the probabilities, we get these, which are just the coordinates in the dual basis. So once we have those, we can use them to weight our Pavum elements and recover our density matrix. But we can actually do a little bit more that will turn out to be useful, interpretatively, perhaps. So we'll begin here by forming a matrix of conditional probabilities. Supposing we repeat our Pavum twice, okay? So in other words, we want the probabilities for each of the Pavum elements EJ that we start with that one, and then we end up with EI, another one of the Pavum elements. So we do the experiment once, you get one of these Pavum outcomes, and then we do it again. Someone just tells you, okay, I did it twice. What's the probabilities for the second outcomes? And so each one of these conditional probabilities is going to be this trace here. So after the first experiment, you're going to be in one of the outcome states of the Pavum. And recall, those are just the Pavum elements divided by their trace. In other words, just they're now have trace 1. So they're like density matrices. So supposing we got this outcome, then what's the probability that we get that outcome? So, iterating over, I and j, we can form a matrix out of all these probabilities. Now, if you think about this g squared guy is just basically being the trace of ei times ej, this is quite related to this Graham matrix thing, but we have this little divide by the trace. Now, we can use this matrix of conditional probabilities to obtain what the cubists call the Born matrix, phi. And it's just the inverse of that, phi. So what's the point? So if we take our density matrix, we have its probabilities. Then if we act on that vector of probabilities with phi, we get these numbers q, which notice sum to 1. So before, when we expanded in the dual basis, these did not sum to 1. Here, they do sum to 1. But notice a negative element. OK, so these are not probabilities, but quasi-probabilities. And which are just a generalization of probability where, the vector has to sum to 1, but there can be negative elements. So once we have these quasi-probabilities, we can get back our original density matrix by using them as the weights on normalized Pavum elements. So we go over all the Pavum elements, divide by the trace, multiply each one by the quasi-probability, boom, we get our density matrix back. Another way of thinking about this matrix phi is that it can be obtained from the dual basis. And in fact, it's nicer to renormalize the dual elements so that they have the same weights as the Pavum elements. So here we're just going to go over the dual and just make sure that the procedure I described before, they're all going to have unit trace. And so if we just multiply them by the trace of the Pavum elements, then they'll have that same trace. And in fact, now the D's sum to the identity, but it's not a Pavum. They're indefinite matrices. OK, so then, whereas before we did E given E, the conditional probability matrix for repeating the Pavum twice, we can now do the same thing, but for the dual basis. So it's the same structure as before. And we get this conditional matrix of quasi-probabilities. And so notice, if we expand our density matrix in normalized dual elements, we get the quasi-probabilities directly without using phi. Oh, sorry. Well, yes, that's true. I skipped a step here. If you look, where was it? Here's phi. And then this one, conditional quasi-probability matrix of the dual element, given the dual elements, it's the same thing. So this is just also phi. OK, that's what I meant to say. And then also, if you don't like phi or whatever, you can just expand in the normalized dual elements to get those same quasi-probabilities. And then use those to weight the normalized Pavum elements, recover the density matrix, or symmetrically use the original probabilities to weight the normalized dual elements. OK. I hope that made sense. There's a lot of, there's several moving pieces here. You have your Pavum elements, and then you can use this frame operator to get the dual elements. And then you take the dual elements and you renormalize them so that they have the same trace as the original elements. OK? So then you can expand in the Pavum elements to get probabilities. you can expand in the dual elements to get quasi-probabilities. The probabilities provide the weights on the dual elements, normalized, and the quasi-probabilities provide the weights on the problem elements, normalized. Alternatively, you can work with this matrix phi, which you can think of as either the conditional probability matrix, supposing you repeated the problem twice, inverted, or just the conditional probability matrix for the dual elements. And then if you act with that matrix phi on the vector of probabilities, it gives you your quasi-probabilities. Quasi-probabilities, like probabilities, sum to 1. So, okay, why should we care? And here's where we get, maybe potentially a little more philosophical, I guess. I mean, this is somewhat of a rehash of stuff we talked about during the cubism meeting, but it'll go through it in a slightly different way here. So we're going to consider two situations. We have a quantum system, and we're going to consider two measurements, A and B. A is definitely going to be an informationally complete problem, and B could be whatever, could be von Neumann measurement. In this case, just for simplicity, it'll be yet another IC, or informationally complete problem. So here they are. We've generated them. How did we do it? We generated some random frame, and then we tightened it. And remember, tight frames are just rank 1 problems, which we can get by just taking the outer product of the frame vectors. So here we have A and B, two informationally complete tight problems. Okay. And then we have rho, our quantum, the density matrix. So we've somehow determined of our quantum system. Is it ontological? Is it epistemic? Oh, who knows? Okay. So as I've said, we can, because A is an informationally complete problem, we can nail down this quantum state in terms of the probabilities for the outcomes of measurement A. So we go through and take the trace of problem element of A with rho for all the problem elements, and we get our probabilities for the outcomes of A. So first, we're going to consider the case where we measure A, and then we measure B. But before we look at the outcome for A, it's like, what probabilities should we assign to the outcomes of B? To figure this out, we could use a matrix of conditional probabilities. The conditional probabilities for B's outcomes given A's outcomes. Here it is. So, we iterate over all the outcomes of B, and we iterate over all the outcomes of A. And then for each outcome of A, we look at A's outcome state, which recall is problem element of A divided by the trace. Just now it's a density matrix, has unit trace. And then we multiply it by B, problem element of B, and then take the trace. So this is the probability that, if we started out in like this outcome of A, we get this outcome of B. And so we get this conditional probability matrix. And it's column stochastic. In other words, it is a conditional probability matrix. So then to get what we want, we can use the law of total probability, which says that if you're interested in the probability of like outcome BI, and the probabilities for A's outcomes, the conditional probability matrix, you simply sum over the outcomes of A, right? Multiply probability of A times the conditional probability of B given that outcome of A. And if you sum over all of the A's, then you'll just get the probability for B. It's the law of total probability. And, here it works, but, it's an interesting question. Is that just a priori platonically true? Or could there be some like result of physics that would suggest that sometimes that's the wrong law to use. And that's what we're going to see. But OK, so here we have it. We had our probability vector for outcomes of A. We had our conditional probability matrix, and we just multiplied them together, this matrix times this vector. And that will give us our probability for B's outcomes, given the fact that we first did measurement A. And so we can check this. I mean, like another way around, like instead of using that conditional probability matrix, we could say like, okay, well, we know A's out, the probabilities for the A outcomes. And we know what state, the system's going to be in each of those cases. So we can form a density matrix. We just sum over the outcomes of A, multiply outcome state of A times probability of that outcome, and then you add them up. And then you get the density matrix, a mixed state for the system after measurement A. And then we can get the probabilities for the B measurement by just going over B's problem elements, taking the trace with this new row that we have, and getting the probabilities. And you see these probabilities, same as we got there. So this was right. This was just sort of self-check, okay? So, we can kind of go this way around. We have our probabilities for A, and then we like work with the density matrix. Okay, so like after the measurement, okay, now it's a statistical mixture. Each of the outcomes of A weighted by the probability, et cetera, and then we can expand in B's elements to get the probabilities. Or we can form this conditional probability matrix, just multiply that by our vector of probabilities for A, and then we get the probabilities for B, given that we did A. So, that, is given the assumption, well, in this case, it's like this assertion, the law of total probability is valid. So the second thing we're going to consider and contrast with the first is like, what if we don't do A? In other words, we just like go right to the B measurement. So we already know what the answer should be. Like we have our density matrix row and whatever, we didn't do A, who cares? Who cares about A? Screw A. Let's just expand in problem elements of B. Boom, there they are. Here's the probabilities for B's outcomes given our density matrix. No A in sight. There it is. That's the answer. But you think about it for a second and you're like, well, the whole point of these like informationally complete positive operator value measures is that the probabilities on those outcomes completely nail down the quantum state. So if we know the probabilities for this like measurement A, I mean, that's just like knowing rho. So you think, well, like there's gotta be a way where we can get like these probabilities for like the B measurement from the probabilities for the A measurement. And it can't be what we did before, where we just like use the law of total probability, because we already did that. And that was for the case where we like actually did measurement A and then did measurement B. So what can we do? Turns out it's very simple. We just form, well, one way of thinking about it, the first way we'll talk about is this Born matrix. Remember the Born matrix, phi, took us from probabilities to quasi-probabilities. So we formed the Born matrix for A. Recall, and then one way of deriving it, we saw several ways of deriving it above. Here, we just go over each of the elements of A and then the elements of A again, and then, basically this is the conditional probability matrix for repeating A, and then we take the inverse. So before, in the case that we like did A and then did B, we just took the probabilities for A, multiplied by the conditional probability matrix of B given A. We got those. Now we'll do something very similar. Okay, it still involves this conditional probability matrix. It still involves this probability vector, but we stick phi in the middle. And behold, those are just exactly the right probabilities. that we got from just using the, the Born rule or whatever. And that's why it's called the Born matrix, because it allows us to recover the Born rule. And notice, everything is still formulated in a way that makes us look as close as possible to the law of total probability. Involves probability of A's outcomes, conditional probability matrix, et cetera, et cetera. But we stick phi in the middle. And remember what phi does, right? It takes probabilities to quasi-probabilities. And now you can see why we wanted the quasi-probabilities, to be as such, as in sum to 1, because then they play nice with this conditional probability matrix. I mean, another way of thinking about this is we could just do B given A acting on the matrix, on the vector of quasi-probabilities. Okay. Another equivalent way of thinking about this is to form the conditional quasi-probability matrix. In other words, motivation here is we could say, well, all right, B given A, phi, probabilities of A. We could multiply phi, we could just sort of collapse that into one thing. And then it would look like then it would look like conditional probability matrix acting on quasi-probabilities. We go the other way around and say, what if we collapse that term together? Then it would be conditional quasi-probability matrix acting on probability vector. So that's what we're going to do. So we can form a conditional quasi-probability matrix. In other words, what's the quasi-probability that you get problem outcome B given A's dual element? What does that mean, conceptually? I mean, since A is hypothetical, you could almost read it as what's the probability that you get outcome B given that this outcome of A didn't happen? I mean, maybe that's the way of thinking about it, But in any case, I mean, it just is formally similar to what we did before. In other words, we have all the dual elements of A. That's what the tilde means here, dual element. Normalize it by the trace there, and then multiply it by B. So here we take problem A, we form its frame operator, we take its inverse, we act with the inverse on the vectorized problem elements, reshape them back into matrices, and then normalize them so that the dual elements and the problem elements have the same trace. And then we form this conditional quasi-probability matrix for outcome B, an outcome of B given one of these, whatever it should mean, dual outcomes of A. And you get this. And you see it's, it has negative numbers, quasi-probabilities. And then we can show, if you recall here, boom, those here's our Born rule probabilities. Here they are again. So we take our probability vector for outcomes of A, we multiply it by this sort of, it's like a conditional quasi-probability matrix, but instead of outcomes of B given outcomes of A, it's outcomes of B given dual outcomes. I put this quotes here because, I interpretively, how should we think about this? And as I said before, this thing, B given A, is just the same as B given A times phi. So that's the conditional probability matrix times phi. And remember, phi was just like that, right? The dual elements given the dual elements. And so, you can see kind of just like an almost equational way, when you multiply these together, the A and the dA's cancel out, just giving you B given dA, which is just that. So, and I don't know if this is actually more concrete or not, but just to summarize all of this, I hope it's not getting too hairy. So suppose, so we have our row. quantum density matrix. We perform problem A. How should we update rho? Well, we take a sum over possible outcome states. We multiply them by the probability that we got that outcome state. Get a statistical mixture. Rho, update rho to rho prime, right? These are the outcome states of A, which are just the problem elements divided by the trace thereof, multiplied by, this is just, like the probability for A, given that we start with that density matrix. So that's if we do perform problem A. What if we don't? What if we don't perform problem A? Well, you can think about it like, well, you do the same thing, but you have those probabilities, but instead you multiply by the dual elements. And what do you get? Well, that's just rho. In other words, this is just the equation for recovering rho from the probabilities of the problem outcome A. Those are the weights on the dual elements. So, I kind of like the symmetry here. It's like, if we do problem A, then we do this like sum over, outcomes each multiplied by their probability. If we don't, and so rho goes to rho prime. If we don't do problem A, we can still formulate things in terms of, this sort of hypothetical measurement A. We have those probabilities, but instead they weight the dual elements. And so rho goes to what? Just rho, nothing happened. And so it's so that's just like the essence of like this reconstruction procedure. And it might sort of seem kind of trivial in a certain way, but then it's just like the interesting part is like the way that these things compose, right? So it's like if we do problem A and then we do problem B, what happens? Well, just like up here, we should update our density matrix to a sum of like, the probability for B multiplied by the outcome state B. How do we get the probability for B? We use the law of total probability. So we sum over outcomes of A, we get the probability for A's outcomes multiplied by the probability of outcome of B given outcome of A. So that's just probability of one of B's outcomes given our updated density matrix here after we do problem A. So this is just this. So we just sort of expanded this in terms of the law of total probability. What if we like don't perform problem A, but then do perform problem B, right? So it's just sort of continuing the theme here. Well, we get an expression that's almost identical, except instead of using this conditional probability matrix for outcomes of B given outcomes of A, we use this quasi-probability matrix, conditional matrix, for outcomes of B given dual outcomes of A. And this just ends up being, probability of outcome B given rho. You can sort of just think about it like I was saying before. It's like you multiply these together, it's just sort of like the dual bit kind of cancels out the A bit there. And then you're just left with probability of B given rho. And then finally, it's like, what if you do neither? Do neither A nor B? You take this and instead, you just have it weight the dual outcomes. Like this is just analogous to this. So we have, probability of A's outcomes times this quasi-probability matrix of dual outcomes given B. And then they weight the dual outcomes of B. But what's that? Oh, that's just probability of, B's outcomes weighting the dual elements, which is just rho, okay? So, what I've tried to show here is that like, this is just the law of total probability, just updating a density matrix. You've done a measurement, you don't know the outcome. What should you assign? This is the reconstruction formula. And you see they're like structurally like identical, except for the fact that here you're weighting problem elements and here you're weighting dual elements. And then it becomes interesting when, you are considering sort of composing measurements, doing one after another. So here's the case where we do A and then B. Here's the case where we don't do A and do B. And notice we can sort of describe what happens in this case, like in terms of the probabilities for the measurement we didn't perform. And this is just sort of like an extension of this, where it's like we didn't do two measurements. Okay. So, as I say, in the first case, we did A, and afterwards we described our system as being in a mixed state of A's outcomes weighted by the probability of them happening. And it's like, now there's no more coherence, there's this classical ignorance or whatever. And to get the, probabilities for B's outcomes, we just used, the old school law of total probability. In the second case, we didn't do A. And so, you can think about it like quantum coherence or whatever was preserved. But, the trick was we could still get the probabilities for this B measurement from the probabilities of the hypothetical A measurement. And one way of thinking about this is that quantum mechanics encourages us to modify the law of total probability. It's not saying the law of total probability is wrong. It just says that there's circumstances in which it's like not quite right. Classically speaking, if we lived in Michael's world where, there was just complete objectivity, where things had definite properties and there was a God's eye view, you could always use the law of total probability, whether or not you did an intermediate measurement A. Because all a measurement does in such a world is reveal a pre-existing property. But quantum mechanically, it's like our interventions matter. It matters that we do A before B. And in the case where we don't do A, we can't regard, A as sort of like having happened. And the beautiful thing is that like we have a rule that's like just as good as the law of total probability. It's called the Born rule. And we can see that it's actually just like almost the simplest generalization you could imagine. If the law of total probability is just written like this, like in matrix notation, probability of B, written in terms of this conditional probability matrix and probability vector, then the Born rule is just written like this, where we stick this matrix phi in the middle. And if phi were the identity, okay, then that's like as much to say there would be no difference between classical and quantum. And you could say the lesson of quantum mechanics is that like phi is not the identity. But of course, this phi is like depends on what pavim you're talking about, okay? So you might wonder, like, what are the pavims? Like, what are the quantum measurements such that like phi is as close to the identity as possible? You could say those measurements sort of witness or identify the irreducible difference between classical and quantum. So with that in mind, we can form a quantity that we'll call quantumness, which is just phi minus the identity. What's the norm of it? And so here's the quantumness of A and B, the two problems we were using. And so, this quantity basically diagnoses the extent to which the law of total probability has to be deformed to give the Born rule, which in this case is like interpreted as like, we have these probabilities for this like measurement we didn't do, but we know they're informationally complete. And so how can we get the probabilities for a future measurement, given the fact that we like didn't do this one measurement? So now it's known that when they exist, symmetric informationally complete pavims, which you'll never guess, correspond to equiangular lines, that's the symmetrical part, they minimize quantumness. And there's a link to a paper that shows this at the end. And if you're worried, the proof that this is so actually doesn't really depend on the particular norm that you choose to measure the difference between phi and the identity. So, if you think about it, it sort of makes sense. It's sort of intuitive in a way that, problems based around equiangular lines, the inner products are all the same. It would sort of make sense that they would have phi matrices that are at like as close to the identity as possible. Now, much of the study of seek problems takes place in the context of, real quantum mechanics, by which I mean complex quantum mechanics, okay? And in that case, seek problems would correspond to complex equiangular lines, right? Like you work in a complex vector space, you can still have lines that make equal angles with each other, et cetera, but it's complex, harder to visualize. And to span the space of density matrices, for dimension D, you would need like D squared of these lines. So, I mean, in 2 dimensions, actually, it's kind of concrete. You can visualize it. You have a qubit, you have your block sphere, and then the 4 elements of the seek problem just make the vertices of a regular tetrahedron. And it's been conjectured and is in fact widely believed on the basis of a great deal of effort that these measurements, seek problems, exist in all complex dimensions. It's been proven in some dimensions. If you can prove that they have to exist in all dimensions, then more power to you. Definitely worth a try. But conditional on that being true, then we know what are the measurements that witness the irreducible difference between classical and quantum. They are the seeks. There's like reasons to believe it's true. No one's ever found a counterexample, et cetera. But here's the thing, right? This entire little talk here, we've just been playing around with real vector spaces. So, we can call them REAK problems, or real informationally complete problems, which, as I say, are the same thing as tight frames. And to be informationally complete, as I say, they have to span the operator space, symmetric matrices, got to have D times D plus 1 over 2 elements. And as we've seen, that's great for, D equals 2. Dimension 2, then you have the Mercedes-Benz frames, got 3 elements. That's, 2 times 3 over 2 is 3. Great. As we've seen in dimension 3, everything's fine. You have like the 6 diagonals of the icosahedron. But then the shit hits the fan. So, over the years, like people have like proved or got bounds for the maximum number of equiangular lines in different real dimensions. And so it's known that like in like most dimensions, there ain't no seeks, okay? There aren't enough equiangular lines to span the space of operators. So here's actually a table. So you see here's the dimension. Here's the maximum number of equiangular lines. You can see that 28 is a popular number here in this world. I don't know why. Here's the dimension of the operator space. And so you see, oh yeah, dimension 2 is great, dimension 3. You look at dimension 7, hey, things are looking good. Oops, 28 equiangular lines, 28 dimensional operator space. And yeah, there is, in fact, like I believe, a connection to the octonians. Similarly, you look down here, you're like, wow, look, dimension 23, there's a seek there. And I believe there's a paper, I should know more about this, but I think there's a relation to like the Leech lattice, that kind of cool stuff. There's these like, kind of exceptional cases where there are enough equiangular lines, but like in general, as you see, this ain't true.
Are you sure that dimension 7 is octonians, not the quaternions?
Oh, did I say quaternions? I meant octonians, yes.
No, I mean, you said octonians, but you were talking about real dimensions, and quaternions, when they're converted from complex to real, I think that they're actually the 7th sphere.
Well, but they would still have 4 like real parameters, right?
Well, I mean, basically you have the 3 Pauli matrices.
Right.
And then you allow with complex numbers.
Let's see. I forget. I should look. I was thinking.
Because I think the unit circle was 1. Then it comes the 7th sphere, which projects in the complex. When it has to come, it could be actually the Octonian 7. I'm not sure.
Yeah, I think it's the octonians. Here, wait.
Right,
So
because you start with 8 and you put the constraint, it's 7.
yeah, right.
And then the quaternions, then the 4th sphere,
Yeah.
you start with the 4 and then put the restrictions, and this is the 3 sphere.
So this is this paper, Sporadic Seeks and Exceptional Lie Algebras. Wait, actually, I think this part, yeah, so here, right, I haven't gone through this argument in detail, but here, yes, like they're talking about the octonians, and here they get incidence matrix furnishing us with 7 equiangular lines in 7, dimension 7. So yeah, little thing going on there. And then
And what did you say was the other 200 and something? Isn't that the monster group?
yeah, right here. So if we fix dimension 23, then you can derive the equiangular lines from the Leech lattice, which yes, leads you right to the monster group. Love it. Love it. So yeah, there you go. And as you can see here, you have these different numbers. Some of these, bounds are not necessarily known exactly.
And we see the string theory 28 lingering around, right?
Oh yeah, you think there could be a connection there? Yeah, why not?
Well, I mean, there's a good reason string theory is of mathematical interest. I mean, also physics, but the main thing is that there's a good argument to say that you can formulate theories that don't have divergences, usual type of divergences. I recently heard people saying, well, they're actually kind of models where you could have divergences at your intersections and kind of specific vertices. But I want to make a few comments, I mean, if it's okay now, or
yeah. I just
are you done?
let me just say one more thing. Yeah. This is like the very end here. Just that it's known, there's the famous Gerson bound, that there can't be more than d times d plus 1 over 2 equiangular lines. Like there obviously in many cases proved to be way less, and this is the same as the number of operators of the dimension of the operator space. So you can't have more. And then finally, just, I just wanted to end on the note of like, so, given that we know that there aren't seeks in all real dimensions, you might wonder, like, what is the next best thing by this metric of quantumness? What are the, special measurements for real quantum mechanics that minimize quantumness or minimize the difference between, the law of total probability and the Born rule? And, that's an interesting open question that I've been thinking about. And in fact, there are all these sort of fascinating differences between like complex quantum mechanics and real. I won't go into all of them today, but surprising things that you wouldn't expect. Like for example, the monogamy of entanglement is like violated. In other words, you can have like multiple systems that are all like maximally entangled, where it's in like normal complex quantum mechanics, it's monogamous. Only 2 quantum systems can be maximally entangled. So there's all sorts of interesting things, and one underlying philosophical issue is why does nature use the complex numbers anyway? So yes, that was just, and then here's the bibliography. Someone's on frames, someone's on the equiangular. This is a nice thesis, and then these are sort of more cubist papers per se. So yeah, anyway, I'm sorry, Vesseline, what was your comment?
Great, thank you. This is really good talk. It's actually matches quite well with the podcast, practically, although you did not advertise it. but one of the points that the guys in the podcast were actually arguing was that, as far as they know, the cubism is coming as close as possible to deriving the Born rule, and effectively that's what you're doing. I mean, this is the justification of the derivation of the Born rule using poems. I was at first kind of concerned, but I'm glad that I didn't interrupt you, because you said repeated same measurements, and I say, yeah, if I'm doing it on the same system, same measurement, I'm going to get the same thing. So I think you better next time say that it's the same measurements of procedures, because A and B are the two kind of same measurements, procedures that you are doing, and that's what you're repeating. It's not kind of a single measurement, individual measurement.
Well, actually, I mean, in this case, you know, if I have one of these poems, like one of these informationally complete poems, and then I repeat it, I won't necessarily get the same answer that I got the first time. Like that'll certainly be true for a standard measurement. You know, you collapse into an eigenstate, then of course you're going to get the same eigenstate with probability 1.
Well, only if you do the measurement quickly enough before something interferes with your system.
For sure. Yeah. In the idealized case where time evolution is the identity. Yeah, definitely. But yeah, I mean, basically the one way of thinking about this sort of relaxation of orthogonality, or like the use of, say, you know, an equiangular frame, what that translates to in terms of the quantum measurements is that, yeah, this idea that like you repeat the measurement and you get the same answer is no longer true. So
right.
You get an outcome, and then actually, you know, there's a non-zero chance that you'll get, you know, pretty much any of the other outcomes. There's bounds on like that, like exactly how spread it has to be. And like, it's often a situation where it's just like, you get this outcome, repeat it, and then it's like, you'll get that outcome like most likely, but you know, yeah, one of the things is like these measurements, the probability vectors can't be sharply peaked. Like if you had just like a probability vector that was just like all zeros and 1, 1, and you said like, oh, those are the probabilities for A's measurement, and then you went to reconstruct the density matrix, it like wouldn't be positive semi-definite. In other words,
right, but that's not actually the correct interpretation. Then the thing is that there was a paper that I came across, and the fact that the first complete poems were actually effectively orthogonal basis, where you're considering things to happen, to expand it. And when I say orthogonal, it's in the sense of mutually excluding events. So if your basis is formed on mutually excluding events, or things that cannot be happening at the same time, then you get the standard definitions and poems. But if you say that actually you are low basis where you haven't taken care to make sure that things are mutually exclusive, then you have to go and form the quasi-probabilities. And this gets you weird numbers that behaves like negative probabilities. But the interpretation of these guys is that, well, because this is the dual, actually, this is the Wigner distribution. Because you remember when you do the Wigner distribution, you're integrating, and the Wigner distribution is your kernel. So the interpretation is that when you have a quasi-probabilities, you're actually working with the Wigner distribution, not with the density matrix.
Yeah, in fact, there's a nice paper I should mention.
While you're typing it, I want to say a few words about the probabilities that we were discussing. Actually, as soon as you go to the place where you are doing the traces, I would say you're doing the standard frequency probability. And then, of course, you put the conditional there. So you're actually merging the two methods together. The only danger is that if you have actually quasi-probabilities, your trace could become 0, which will give you a trouble, because when you cannot divide by 0. And that's where the kind of neat approach is that if you match the poem trace to correspond to the quasi-probability, to the dual space, you define it, because in the standard problem, it's well defined and you don't have problem with traces, then it guarantees that the traces of your quasi-probability would also behave properly. And then everything is okay. So basically you're figuring out a way out of these singularities. But one thing that I'm kind of puzzled is the fact that the Born matrix is built from A and B. And then
no, it's just built out of A, or just one of the problems.
But
you see here, I go over the outcomes of A, and then also outcomes of A again, and then take the trace, then the inverse.
okay, so
So
that
yeah,
there wasn't actually
is associated with like that first measurement that you do.
Okay, then it's good, because I was concerned that if you're taking A and B, these are two things. So basically within the same choice of measurement basis, whether it's nice POVM or SIG POVM, basically you still have a well-defined Born matrix. And then from there, I mean, you can go and look for the quasi-angular lines, always to kind of redefine. I think that this is in effect, in machine learning, when you're trying to group and cluster data points and separate different things. I mean, you're looking at extra dimensions so that you can really cut with a line or with a plane between the two sets and say, well, this is one group and this is the other. Effectively, with quasi-equiangular lines, you're kind of creating the same thing, because you're just choosing to find the formulation of your basis where this is happening. And you're saying that in this basis, this is the most close to classical, which means that practically almost all the probabilities from this kind of lines would be probably about the same, just like when you throw a dice, right?
Yeah. It's like it's like this is like the probabilities are as close to the quasi-probabilities as possible.
Right. Yeah. So then it's interesting about what you show at the end, the connection between what is the number of lines that you can define and the dimensionality of your space. That basically there are only few dimensions that they can match. Most of the time, what you will find that you have less lines than dimensions, which will tell you that you have incomplete information, basically. And it's nice that it seems to be related also to simple theorems in mathematics, in algebra, where you have only these specific fields where, I mean, you can comb the fields on the spheres. So I don't know, when usually mathematically the interest point of view is then like string theory. This is just a nice mathematical space to play around, because you shouldn't have any difficulties with divergences or not being able to comb the sphere. But then I don't know in general, I mean, how things would be justified. And maybe that's kind of the reason that one can say quantumness is actually happening when you have less equidistance lines, much less than the dimensionality of your space. So that's really kind of kills you.
Yeah, I mean, of course, I mean, normally we're working with the complex, or the normal quantum mechanics. And there it's very interesting that, like, unlike in this real case, no one's ever been able to find a dimension where the equiangular lines don't exist. It's like, I mean, it's sort of an interesting question. Like, what is it about working with the complex numbers that suddenly allows, or seemingly allows, for you to have as many equiangular lines as the operator?
Oh, you're saying that if you work with complex numbers, then your operator space matches your equi-lines?
Yeah, so far as anyone knows, that's the case.
Well, I wouldn't be surprised, and the reason is the following: that basically, I mean, the complex numbers the last commutative algebra. I mean, and there is a theorem that says if you have anything that looks like complex numbers, it is isomorphic to the complex plane.
No, I know what you mean. It's just like complex numbers are beautiful from a million different perspectives, it's just like, fundamental theorem of algebra, like division algebras, all this other stuff. And then you're like, how do you make it connect? You know what I mean? It's just like, yeah, I completely agree. Like somehow it's intuitive that it would like have to be true, but no one.
But then
this conjecture was
the interesting thing is that if you look at the entanglements and you're working with complex numbers, basically you write equations which are obviously impossible to be solved in the complex numbers, just because of the order, and that if they commute, then you cannot satisfy them without being them zero. But then if you actually kind of leave this space and say, well, what if I want these coefficients to be non-cumulative and to throw them into quaternion algebra, then you can actually have a solution to these equations.
Right.
And that means that now I'm having the feeling, like you said, that if you do real, basically there is a multi, you're breaking the monogamy of maximally entangled states. That has to be two. It could be more. So you get polygamy there. You go to complex numbers.
Yeah, exactly.
Yeah, you go to complex numbers. Now you're forced to actually have monogamy. But as I said, you can break the problem with the entanglement if you go to quaternions. Because quaternions would give you a way to solve the conditions that otherwise you wouldn't be able to solve with commuting complex numbers. And I know that there are papers that are claiming that there is no entanglement in Clifford spaces. So which is consistent with you start with the real one, monogamy, polygamy, you have a what complex, you get only one specific type, and then you go to the quaternions, and no, there is no entanglement anymore there.
Huh. Oh, that's interesting. Yeah, that's a cool pattern.
Yeah.
And I think there's been work on, I forget where, maybe I'm wrong, but like, the generalization of the equiangular line stuff to like quaternionic. Is that even possible though? Quaternionic space.
Well, my guess is then it should collapse all to the weird number 4. And that's my hunch, is that this would be the answer if one space-time is 4-dimensional. But I haven't seen all the kind of nitty-gritty math that has to come up there.
By the way, you might be interested in, well, this paper, but also several others in this vein. There's these interesting connections people have been drawing between the complex equiangular lines, or the complex seek pathms, and some, questions in, like number fields, algebraic number theory. And yeah,
I will suggest then when you start your studies, and if they ask you to pick your research topic, try to say that you want to generalize this to the quaternion space and see what you get.
For sure. Yeah, definitely. And then this paper is also nice, where they sort of make this whole quasi-probability stuff, look as close to the usual like Wigner type constructions. Yet another great paper from John DeBroda and Blake Stacy. Yeah, sure, I should put these in the chat. Well, thanks for your great comments and questions.
Well, great talk. Actually, I realize I should have asked you to post it in the group that we are trying to push. Somebody from the quantum AI and ML group here, which is now actually international, would have had interest. And I don't know how I forgot. Because usually I try to cross-post and advertise similar meetings for other people to join. But feel free in the future. I mean, when you're preparing your talk, and then just post it also in the other group, also the machine learning and quantum computing.
Well, yeah, because I'm interested. I don't, like I brought up the grid cells, or at the beginning, and it's like because I had found a paper. I mean, like when I first was like reading about the hexagon and the Mercedes-Benz frame, I immediately thought of that video of the mouse, which like I had seen years ago. And then I ended up finding a paper where some people do actually try to analyze that, like in explicitly frame theoretic terms. And obviously it's not exactly like what we talked about today, because like it involves like a whole lattice and lots of different frames and stuff. But it speaks to like, I mean, to the degree like a biological system is, having evolved by chance, and is, it's just really about how do you get precision out of messiness? Like how do you harness the power of like, large numbers and so forth? Like it makes sense to me that both in biology, things like frames would be really useful because of their redundancy. And then also similarly, like in artificial intelligence. And so I'm like interested, like some real AI experts. Like I'd love to know if people thought about, the interconnections between these like frame representations and, the kinds of representations that are learned by neural networks or whatever. Like under what conditions will a neural network tend to learn a kind of over-complete representation, and like for what reason, and that kind of stuff. Like I'm sure there's a lot of interesting stuff you could figure out there. And then I hope to do another meetup next week, sort of expanding on this a little bit, talking about more generally operator frames, and so-called tight operator frames, different from tight operator frame. And there's these interesting connections to so-called design theory, spherical designs, and all sorts of interesting goodies. So yeah, well, continue on with a similar theme next time.
One thing that I kind of caught my attention in your talk was when you had Hermitian matrix. What was the type of frame that you were defining?
Oh, well, just that you would need like d squared elements in your informationally complete problem. So like for 2 dimensions, you'd need 4.
I mean, you started with a tight one, and then you had the other equiangular, but in between there was also the version where you had the Hermitian matrix that was involved.
Sort of, yeah. So that was just the tight frame, and we actually didn't use the Hermitian one. Like in other words, we just randomly generated a frame, and then like decomposed it, right? In the polar decomposition where you compose, you get like a
right
times a Hermitian, but then we just threw out the Hermitian one.
Well, actually, that's where I think it's interesting, because you see, to me now the interpretation is that this orthonormal U basis, this is the basis of mutually exclusive possibilities, and eventually all the observers would kind of,
Well, no, because here it's sort of it cuts across the grain. Like in other words, here's the frame. This is the 2-dimensional vector. Here's an element. There's an element. There's an element. There's an element. There's 5 elements, and then like the problem would be formed from the outer products of each of these 2-dimensional vectors with itself.
Right, but what I'm talking about is the interpretation and understanding what is really going on there. The orthogonal part U will tell you basically what are the mutually exclusive outcomes, and eventually all observers would kind of agree on that sooner or later. Because if somebody finds something that nobody else has seen it, they'll come and see it, or I mean, they will disprove the observation. So you will arrive at that one, and now the question is, what about the Hermitian H part of the frame? And that's interesting because this Hermitian H part, I mean, from standard quantum mechanics, is observable. So it seems that if you're an observer with such a frame, then it should something tell about your frame, not about the process itself.
So here's the thing, though. The outcomes, as I say, correspond to the columns of this matrix. Okay. And so, this doesn't correspond to an outcome. Like this doesn't correspond to an outcome. Those are just two of them. It's these columns that correspond to outcomes, but it's these which are orthogonal. The thing is, the condition that these be orthogonal corresponds to the Pavum condition itself, that the elements sum to the identity. In other words, the fact that the outer product of this guy with itself, 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 that they all sum to the identity is the same as saying that this and this are orthogonal. So in other words, if you had that Hermitian there, it wouldn't be a tight frame, and so it wouldn't form a Pavum.
Okay, so then basically, I mean, you can throw away the Hermitian, right?
Yeah, like you have to in order to get like.
And one way to throw away this Hermitian matrix is to do a measurement to its meaning and get a number and collapse your state. So now your observation is in a system with a specific value of this Hermitian matrix, and then after that you're Pavum. And my point is that this is something interesting because this H seems to carry some information about the observer, not about the system.
Yeah, it's an interesting point. I hadn't thought about that. Like, because actually I was recently thinking about sort of like the relationship between some of this stuff and weak measurements. So for example, like I was thinking about, well, you have these dual elements and, they're not positive semi-definite. They're indefinite matrices. So, you can't interpret them as density matrices or outcomes really. But like, you could do what we just did there, right? Like do a polar decomposition, split it off into like a unitary part and a Hermitian part. And then like you can do a trick where you do a weak measurement where you like prepare some state phi, measure the Hermitian part, but then post-select on basically like that unitary times phi. And then you end up basically with a bracket that's like phi, the unitary times the Hermitian, and then phi. But the unitary times the Hermitian is just your original dual element, like which is indefinite or whatever. And so using a weak measurement, you can actually like measure a non-positive semi-definite matrix. And so I wonder, if there's a way of thinking about things where it's like, okay, a Pavum has to sum to the identity, but like maybe we can generalize it where, they don't sum to the identity, but you sort of like do like a weak measurement in there, okay? Like using like that Hermitian thing or something. And then, effectively the whole thing is like, it's not a tight frame or whatever, but like individually, you could kind of split it off into like a part that's a Pavum, that's a tight frame, and maybe like a weak measurement somehow of that Hermitian matrix. I mean, that's making me think, that's like a very interesting point. There might be something there.
Yeah. Mm-hmm.
Maybe I was too quick to throw this guy away. Any other thoughts, comments? I noticed Michael has been weirdly quiet for a while.
I think he's speechless.
Speechless. Just can't handle it.
Okay, I will let you continue with the discussion. I hope that I didn't interrupt the usual kind of
No, not
conversation.
at all. No, thank you for coming. No,
Yeah,
you're-
but I have to go get ready for something that just my family said that we have to do.
Cool.
But it's great talk, and then I'm looking for the next one that you. And if remind me, I mean, probably on Thursday when we're meeting, to find. I will be trying to get this paper on the Wigner distributions. But I don't know where was it. I mean, why was I coming across my desk? And so I will try to get it. And if I didn't send you a link or something, just remind me.
Okay, yeah, we'll do.
Yeah. Okay, bye everyone.
See ya.
Yep. Bye.
Well, yeah, thanks again for coming, Marty.
You're welcome.
Again.
I really contributed a lot. No, actually, I was thinking about the brain and you're talking about dimensionality, that the brain actually doesn't just use synapses and the strength of synapses like Hebbian learning. It also uses time. The sequence, you know, of neuron firing is an extra dimension that it could be using.
Yeah, right. It's often, yeah, phrased like, you know, a neuron's going to like be firing at a certain frequency.
Yeah.
Stimulus, but of course it's actually, yeah, it's like it's more stochastic. And
Yeah.
you know, and of course, like the exact sequence, the exact time sequence matters because, you know, when a neuron synthesizes stuff, like it depends on whether, you know, the two signals like enter in like within a certain time interval.
Right. Yeah, and it's the oligodendrites that arrange for the timing to synchronize.
Interesting.
So that's a type. It's a, there's like 5 different types of cells, and I'm wondering about spindle cells that only apes have.
Yeah, spindle. Yeah, wait, I remember reading about spindle cells. What is that? Yeah, that and glial cells.
Well, yeah, there's 5. I think there's 4 types of glial cells. Yeah, specialized cells. They look like spindles. That's why they're called spindle cells.
Huh. Are spindle cells normal? Yeah, mainly getting the cancer version of spindle cells. Okay. Prognosis is grim.
Yeah.
But yeah, I mean, it's like, you know, you just think about evolution and the way that, you know, it's like how do information processing systems like arise out of chaos, basically.
I know.
It's like they can't, you know, so much of our, you know, mathematics is based around like a kind of minimalism because, you know, we're human beings. We're trying to use a minimum of symbols. You know, we only have pen and paper for so long, right? And so of course you're going to use Cartesian axes because they're the most efficient representationally. Because, and you know, you don't have to worry about like losing one of the coordinates. I mean, you just wrote them down or whatever. I mean, it's, but you know, when you're thinking about big noisy systems and stuff, it's not so much like the minimalism that's going to be selected for, but like redundancy, like redundant.
Yeah, it's kind of, yeah, redundancy makes it error correcting. Oh, here's Michael.
So did I hear somebody say that we evolved out of chaos?
Oh yeah, I think so.
Well,
has anybody heard of self-organizing systems? What do you think of that, Matt?
Yeah. I mean, my favorite example is the sand pile. You know about the sand pile model?
I wasn't allowed to go to the beach. I don't.
No, this is like my favorite example. One time I coded up years ago, like a little 3D model of this. But yeah, it's like one of my favorite examples of a self-organizing system because it's so ridiculously simple. It's like literally a pile of sand. Like in other words, they've actually done experiments like with real sand piles, but the easiest way is to consider like an idealized model. So picture a table that's been like gridded up, and then at each like time step, you drop a single little piece of sand, and it just like sits at one of the spots in the grid. Drop in sand at random. And the idea is like, okay, drop a piece of sand, drop another one, there's 3. And then when you drop the 4th, they topple to the 4 sides, okay? And then finally, the rule is that like if a sand reaches like the edge of the table, it falls off. So you have this like incredibly simple rule. Sand falls at random. If there's more than, if there's more than 3, get the 4th piece of sand, it topples. And then, so sand is entering the system. Also, sand is leaving the system, right? So it's, one of these non-equilibrium systems. Energy is like flowing through it. And you have this very simple rule. And what's interesting is like, okay, you start sprinkling sand around, and okay, you have a little avalanche. You add the 4th, it topples. But after a while, you add enough sand that like, okay, one topples, and then it topples into another one. Okay. And then after a while, you get, topples into one, topples into another, and you get these chain reactions. And what's really interesting is like invariably, like if you just keep adding sand, eventually the sand pile will reach a critical state such that adding one more piece of sand could lead to an avalanche of any magnitude. In other words, it could lead to a tiny avalanche, could lead to a humongous avalanche, it could lead to a middle, like an avalanche, like at any scale is like more or less equally likely if you add just one more piece of sand. And, and that's quite like a system, a self-organized system like our brains, which is keyed up, right? Like I just need like a single stimulus. It could lead to like, oh, I don't care about that, swat a fly. Or I hear a single word and my heart's broken, avalanche. Like, so yeah, one of my favorite examples of these sort of self-organized systems where you get this sort of scale-free dynamics is the sand pile, the Abelian sand pile model.
Well, there's always a tipping point or a phase transition. Have we discovered the cure for spindle cell sarcoma? What am I looking at here?
We were wondering.
Am I going to get the Nobel Prize in Medicine? Oh God, that's disgusting. I hope I don't have that. Looks like something I ate last night.
Well, I assume I guess the purple is like whatever dye they use. But
yeah.
It does make a heck of
I think the purple means you're dead.
Purple gang. Yeah.
What did I miss? I was called away on an emergency, so I haven't been around. Right. Did I miss a lot? Will I be culturally deprived going forward, or?
Well, I'll upload the video. We began. We talked about frames, and then.
Yeah. So these are in your notes. I mean, yeah. This is all. Yeah.
You can play this again, and it's recorded.
Yeah, I would say, there were 3 sections. First was about frame theory, where you're like using these sort of more flexible, overcomplete bases for, vector spaces. And then we talked about like operator frames, where you use the same kind of technique to kind of coordinatize the space of operators, or like in quantum mechanics, density matrices. And then the third part was sort of like talking about, the nature of, a certain way of using the probability calculus that quantum mechanics encourages, so that you look at.
Of course, I don't believe any of this stuff. I'm just here for laughs. Yeah. What happened to Moshe? Moshe. Oh, he's probably preparing for tomorrow. More laughs. Yeah, New York Quantum Meetup is meeting tomorrow. The second half of his presentation.
Nice.
which
Yeah,
he's actually given about umpteen times before. But because the other two guys, Barry, Barry, and Sid, Sid Harda, the Indian guy.
Yeah.
Yeah, they're both in the middle of presentations, but they also have other work that they do, so they haven't been able to present for a while. They kind of started their series of presentations, but so Moshe reverts to his filler that he always does, which
he'll get there.
to me is a comedy routine, because I don't believe any of this stuff. I believe in objective reality. I do not believe in probability, as you well know. But the math is interesting.
Yeah, well, I mean, I think that, well, one thing that's I feel like is true, whatever your interpretation is that, quantum mechanics seems that it wants us to think about counterfactuals in a different way. I mean, just in the concept that measurements lead to disturbances.
As opposed to classical physics?
Yeah, I mean,
why so?
Because in classical physics, in general, there's always a kind of measurement you can do that's sort of passive.
But don't you understand why? This all has to do with the theory of measurement, not objective reality. In classical physics, the idea is that the measurement is not disturbing the state.
Yeah.
But in quantum physics, when you're doing a macroscopic measurement on a micro state, it's obviously going to disturb the state.
Yeah.
So this has to do with measurement theory, not objective reality.
Whatever your interpretation is, quantum mechanics is you have to be very careful in talking about counterfactual situations. I'm not making the claim right now about objectivity or anything. I'm just saying it's because of that disturbance thing, whether you want to interpret it in however way, it's just, you have to take counterfactuals.
But there are theories that, obviate that. Bohm's theory does away with all this probability stuff. Bohm's theory is completely deterministic.
I'm just talking about the way that counterfactuals enter the theory in a different way.
But this is in our minds. I mean, we have to distinguish between objective reality, nature's objective reality, and our ability to interpret what's going on. Because we don't have the technology or the intelligence to figure out what the objective reality is. It doesn't mean that the objective reality doesn't exist, right, Marty? I know Marty agrees with me.
I am barely following what you're doing, what you're saying.
Objective reality. It's an English expression.
Yeah.
As Yogi Berra said, you can look it up.
Yeah, again, I'm just saying I guess I was thinking more about what David or whatever had been saying, you know what I mean? About basically it's not ever really worth thinking about counterfactuals in a fundamental theory because the world's just the world and it couldn't have ever been any other way. He was basically arguing that everything is just necessary or something.
You're talking about David Chang.
Yeah.
I'm surprised you remember him because he hasn't been here for a while. But you're probably following the emails that we send each other.
I've been staying away a little bit, but yeah.
How much trouble am I in for those emails? I mean, I'm waiting for the Homeland Security Department to knock on my door in the middle of the night.
But he just made this claim that counterfactuals should sort of be banned, from how we think about the world.
No.
And I just don't know if that's true. I mean, and again, I'm right now being agnostic about these issues about subjectivity or objectivity or whatever. I just mean that it seems if you just ban talk of counterfactuals, it's difficult to even formulate a lot of these interesting questions that quantum mechanics sort of.
Well, let me tell
Oh,
you
yeah.
something about David. I think I know him better than probably anybody at these meetups, because we talk a lot, and we also we're in tune with each other's ideas. I mean, we basically have the same philosophy. I don't think that he has the technical expertise that most of us have. His thinking is more high level, although I do agree with what he says. And what he's saying about counterfactuals, it may help you to think, but there's no such thing as a counterfactual. There are only factuals.
Yeah.
That's what objective
Okay.
reality is. The fact that we don't know how to interpret objective reality is our limitation. It's not nature's
Is that really,
limitation.
I wonder, is that true?
Yeah.
Objectivity imply there are no counterfactuals? Because like you could imagine like a world where there was like a necessary element of subjectivity, but where there were no counterfactuals. I mean, you know what I mean? Like, I don't know if those two concepts are exactly the
No,
same.
but you said imagine the world, but the real world only has factuals.
Well, I'm
at
just saying
at
that
any instant of time.
counterfactuality doesn't necessarily imply objectivity and vice versa. Like, you know what I mean? Like, or like the lack
Yeah.
of.
A counterfactual could be real.
Then it's a factual.
Yeah, but I think it's a superset of reality and non-reality. It's I don't know. Just I think that I don't know. I think in terms of our brains, we think in terms of meanings. Like things are stored in our brains as meanings, not words. We have like an entire story in our brain for every meaning.
Yeah, absolutely.
And when you're talking about these dimensions like today, I was thinking, yeah, that's like the brain makes up dimensions, categories of like colors, categories of shapes, and it combines these to make meanings. And that's what I think. We don't have any encoding system other than that, and it's all just associative memory. Whatever, it's like winner take all, then it comes out as a word from our storytelling section of our brain.
But this is the point. What our brains tell us is reality is not objective reality. We are limited. We are limited. What I'm saying is nature has an objective reality aside from anything our brains tell us.
Yeah.
And we can only hope to get close to interpreting that objective reality. But to say that nature is probabilistic, to me, is just doesn't wash.
Even though two people can agree on something, doesn't mean they're not both wrong.
Well, that too, but it's also because they're human.
Yeah. Oh, yeah.
They're not perfect.
And they evolved. Yeah.
And there are a lot of things that go on in the universe that we're not aware of because our evolution did not depend on it. Like, for example, electromagnetic waves, radio waves, were not discovered until 150 years ago because there was no need for us to know about them because our evolution did not depend on it. So we did not develop sensory mechanisms, sensory organs to interpret electromagnetic waves, except for a very small portion of the spectrum, except that light spectrum.
Yeah.
Except that everything is electromagnetic waves. And so we are sensing them. We are sensing electromagnetic waves all the time, every sense.
Yeah, for sure.
Touch, sight, smell, everything.
Right. But like the idea that electromagnetic waves are related to magnets and lightning. I mean, that was like mind-blowing. I wish I would have been there when Maxwell was like, he worked out his equations and, plugged in the, different constants for the electromagnetic field and then was like, oh, there should be an electromagnetic wave, and then like calculated the speed that it would propagate at. And then like, lo and behold, it was like the recently measured speed of light. Like,
But even Maxwell didn't know about radio waves. Radio waves,
Oh.
microwaves. This spectrum of electromagnetic waves was not known until about 150 years
Yeah,
ago, or
uh-huh.
130, 40. And because there was no reason for us to know that, our evolution did not depend on interpreting that. Our evolution did depend on interpreting the very narrow band of the electromagnetic spectrum, the light band. But the whole rest of the spectrum wasn't necessary for our evolution, so we didn't know about it.
Yeah, it's like we have the tools that we have. You know, we have like both, you know, what evolution gave us and what we've learned, and you know,
But we still don't know. We still don't know the half of it. There's a
yeah,
lot more. As Hamlet said to Horatio, there are more things in heaven and earth than are dreamt of in your philosophy,
yeah.
you illiterate people. And
Yeah,
maybe we will never know the ultimate reality because our brains, albeit our brains are probably the most advanced computer in the universe, which I believe, they're still not the ultimate. You know, they are not, I don't think our brains are capable of interpreting the ultimate basis of nature.
Oh, wait till 6G comes out.
Yeah, wait till 6.
Yeah, right. We're still waiting for 5G. What are we gonna do, jump over 5G?
No.
Go straight to 6G.
They're working on it.
Yeah, they're working on it.
They are 6G.
If we don't blow ourselves up before that happens, which, see, this is why I believe that extraterrestrials don't exist. I believe we are the most advanced civilization in the universe, because once they reach our level of technological sophistication, they destroy themselves. That's a universal factor that you can take to the bank.
That could, yeah.
I've heard it said, yeah. All right, guys.
I don't have children to worry about, so I don't really care. You have any children, Marty? If I had children, I'd be worried.
I have one. I couldn't afford more.
Well, I couldn't afford any at that time, but now that I can afford them, now I don't want them.
Yeah, well, that is the paradox.
I didn't like myself as a child. That's why I never liked children.
Oh, well, that's a good example.
Maybe I should save this for my psychiatrist thing.
Yeah.
What happened to Moshe? Oh, yeah, he's probably rehearsing his for the umpteenth time. He's going to talk about whether potential energy is absolute or relative. Give me a break.
Yeah, well, potential energy.
Of course, it's relative.
Yes.
But I think he's also going to try to talk about whether kinetic energy is absolute or relative. I don't know. I think Isaac Newton kind of established that. I don't know if Moshe is going to be able to add anything. Are you guys coming tomorrow?
I unfortunately cannot. In general, I don't know, these Sundays have been tricky.
No, I may just go for laughs for the same reason I come here. But I couldn't stay for the whole thing. I had an emergency. I had to go out and catch the last rays of sunlight before the tornado comes.
Oh,
whatever is
bad
predicted.
weather later on this week.
It's a beautiful day.
Yeah, it's beautiful here.
Too bad you had to be, stuck doing this.
Oh, I got my window open.
You got your window open.
Yeah.
It's not bad today.
But, it's a beautiful day. Spring came in a day early. But
well, it's classic March, it's just like been.
Yeah, it's probably going to be nice tomorrow too. I'll probably boycott Moshe. I could probably recite it by heart anyway, what he's going to say.
Yeah, just
I've decided not to go there anymore because I can't understand a thing. I mean, this one, at least I can understand the linear algebra sometimes.
Why can't you understand?
No,
I think this is a lot more complex.
Oh yeah, I like complexity.
What don't you understand about what he says? I understand everything he says. I just disagree with everything.
Oh,
So-
yeah, it's hard to relate to me the matrices and all to actual physics. When someone talks about like particles, I don't understand how that relates to matrices at all.
Well, Moshe is mainly into black holes. You know, the information storage in a black hole. I don't believe any of this. I don't believe any of this black hole theory.
Well, but I should. Well, I should.
No empirical evidence, and the theory. There's a lot of physics and mathematical flaws in the entire theory of Hawking radiation and all this other stuff.
Well, here you'll love that. Yeah, I should email this to the list. The email.
Oh, quantum gravity. How do you know that gravity is a quantum theory? Can you show me a graviton? You got any gravitons laying around there?
Well, I bring up
There are physicists who think that the graviton has actually been discovered. I don't know that gravity is a quantum theory. There's no evidence.
Well, okay.
No empirical evidence. Maybe mathematical fantasy, but no empirical evidence.
Well, I just wanted to say that
Yeah.
It's coming up on like the 1-year anniversary of me, starting these meetings again. And if you recall way back when, like the first thing that we talked about was these like simple qubit models of wormholes. And that was all based on the paper Quantum Gravity in the Lab, Part 1. And
which lab is this? Is there a lab in New Jersey that's discovered this?
Well, remember, we could build them out of qubits.
Gravitons?
Well, I mean.
Well, but this is all conjecture. This is not reality.
Well,
You can build any fantastical universe you want.
No, remember what it was? It was the idea was to like use a bunch of qubits to model like two entangled black holes by using systems that had like very chaotic Hamiltonians, so that they were very fast scrambling. And then there was like a generalization of the teleportation protocol where, you would sort of like throw in a qubit on the one side, remember it was like evolve this one back in time, and then kind of like load in a qubit, evolve it forward in time. And then there was like a classical coupling between the two sides. And then you evolve this guy forward in time, and then the qubit would pop back out.
But you know what the key word is here? You said model. Yeah, anything you do on a computer, whether it's a classical digital computer or a quantum computer, is a model.
Yeah, exactly.
Doesn't necessarily correspond to reality.
Yes.
How do you know that a black hole respects the teleportation protocol or any other protocol?
How do you know what to look for? You got to use your models. So these are models.
Yeah, but what I see is a black hole is a dead object with zero entropy. The only thing that characterizes any black hole we've ever observed is mass and angular momentum.
Yeah, so this starts from a different...
And hypothetically electrical charge, but in the real universe, they probably don't exist. So that means the entropy is zero. All of these theories are based on entropy being greater than zero. Okay. I say a black hole has zero entropy. I stick with Stephen Hawking's original supposition that information is destroyed in the black hole.
All I'm saying is they, yes, have certain assumptions. A, you're going to assign a quantum state to the black hole, and they're going to model the black hole dynamics using like a fast scrambling.
But these are fantasies. There's no empirical evidence for any of this.
Well, but you propose a model and then you find its consequences, and then you go.
This is math. This is mathematics. Well, you can invent any universe. How about Malthus is ADS-CFT? Have you ever seen an anti-de Sitter universe? An anti-de Sitter universe would collapse faster than you could say Malthus.
What's cool is that you can use your quantum computer to simulate like a little anti-de Sitter.
Simulate. That's the key. Simulate.
Right.
And by the way, you can simulate quantum theory on a digital computer. You don't even need a quantum. You can simulate entanglement on a digital computer.
Yeah, like you can do it way better here, right? So like
you can do it way better, but again, it's a simulation. That's the key word. It's a model. It's
no
not
one,
reality.
no one's denying that, right? Like the point is that we're trying to understand black holes. And so the question is this theory valid? And so they're going to use models in order to draw out consequences in order to.
But you are trying to understand black holes with zero empirical evidence. Like I said, the only empirical evidence we have is that a black hole has mass and angular momentum. End of story. Until I have more empirical evidence, none of these models are worth a damn.
Well, but you're looking at, I mean, think about like astronomical data, you know, like two black holes going around, there's some gravity waves and stuff. And
gravity waves are classical. Gravity waves are predicted by Einstein's classical GR.
My larger point is that what's bad about your picture of the black hole as being like a dead and simple object, and good about their picture of a black hole being this complicated quantum object, is that these sort of results might actually have real world engineering implications when it comes to designing condensed matter systems. In other words, we're trying to like engineer these things, and this like idea that like you can throw something in one and then it can like teleport out the other one, et cetera, might actually be useful. So you can kill two birds with one stone.
Okay, and I'm not saying that all of this mathematical conjecture is a worthless pursuit. I'm not saying that. It may be worthwhile. Yeah, if you can relate it, if you can relate ADS-CFT to condensed matter physics, then it's a worthwhile pursuit. But there are physicists who believe all this bullshit about Hawking radiation and wormholes and hidden universes. You know, it's called garbage in, garbage out. We have no empirical evidence for any of this. So any theory you derive from this conjecture is also just conjecture.
Yeah, but like look at their language here, right? They say, we discuss how quantum gravity may be simulated using quantum devices. And then they don't even say black holes or.
But there's no evidence for that gravity is a quantum theory. Where's any evidence that gravity is a quantum theory? The best theory we have of gravity is Einstein's GR. There is no evidence that gravity is a quantum theory.
They say in the paper, they're like, okay, you have this system and it goes in, right? And then it gets scrambled out. And then like later on, somewhere else, it kind of like unscrambles and then pops out. And you're like, what does it remind you of? It reminds you of like something getting really, really close to a black hole and getting redshifted, then like scrambled out over its surface.
That's all classical. That's not quantum.
And then the other one gets, you go to the other black hole that's entangled and it unscrambles and then the thing pops out. In other words, it's an analogy. You're like, wow, that's like sounds exactly like what you would expect to see if like something got close to a black hole and then it popped out somewhere else. And then you'd be like, well, either it just teleported instantaneously or
let me ask you something. How do you get a black hole is the densest object for its volume. So how do you get inside of a black hole? The only thing, by adding mass to a black hole, you're increasing its volume because a black hole is already the densest possible mass that you can have for that particular volume. And this, I've had this argument with Moshe over and over. He talks about a black hole being empty space. How can a black hole be empty space?
Oh, well, but that's certainly true because it's like.
Well, then how can you add anything to a black hole? How can you add matter? If you add matter, it causes the black hole to grow.
Is that a problem? Or like, what's the problem?
It's a black hole is a completely classical object as far as the evidence we have. Now you can conjecture that it's a quantum object, but the evidence we have, the empirical evidence, is that it is a classical object. It is the most basic classical object. It's got two parameters. It's got mass and angular momentum, which means, according to my calculation, K log W is 0. The entropy is 0. And all this black hole thermodynamics theory is based on the entropy being other than 0. I don't believe it. There's no evidence for it. Yeah, you can invent, you can conjecture and invent all these imaginary theories.
I didn't it.
But
Like,
until we have some empirical evidence, it's all bullshit.
like in general relativity, now I don't even know that much about general relativity, like in very concrete terms, but like, okay, so you can have, right, it's like, so you can have purely gravitational objects because, the gravitational field has a kind of self energy. And so if you have like, as I say, gravity itself gravitates. And so you can imagine, there's like this configuration where there's like no matter, but like there's still this like black hole or whatever, as opposed to normally thinking about like, okay, there's matter and energy, and then they're like kind of curving the space-time around it. But so then like, why can't you just think about it like some matter and energy falls in? And I mean, like, I don't know what you mean. Like even classically, it's just like, you could have a situation where it's just like not, where it's just like.
Well, this theory, let me tell you something.
Matter
This
and there's
theory about massless black holes, that, that a black hole could just be some curvature of space-time. It's a remnant of the Big Bang. It's
No, I
just
mean,
a
like,
curvature of space-time without any mass
I mean, like,
being present. This is all conjecture. There's no evidence for this.
Sorry, you just said, I mean, you were like, gravitational waves are classical GR.
Yes.
What's a gravitational wave made out of? It's like made out of gravity. Same thing as a black hole. It's like it's made out of gravity. It's like the same thing.
No. But a gravitation, and Moshe also tried to use this argument about the LIGO experiment proves the gravity's a quantum theory, and I had to correct him.
No, I'm not talking about. No, sorry.
Gravitational waves are purely the result of Einstein's classical GR theory.
Yeah, no, I'm sticking with that. Okay, I'm not talking about quantum at all. I'm just saying, like.
So what are we proving here? We're not proving that gravity is a quantum theory.
You just said that that a black hole couldn't be just a gravitational phenomenon or something.
Well, that it couldn't just be the curvature of space-time.
Yeah, why not? Like,
why not? Because there's no evidence for it.
Oh, I'm giving up. Sorry.
It's highly conjectural.
No, it's like
It's been 3 hours.
Show me a black hole that doesn't have any mass. It's just curvature of space-time.
What are you talking about?
There's no empirical evidence for it.
What are you talking about? No mass, like
Bye-bye.
mass versus energy, like doesn't matter. Like a gravitational wave is just space-time curvature.
Well,
that same.
First of all, I hate to burst your bubble, but let me burst the entire bubble of special relativity and general relativity. There are other ways to interpret the curvature of space-time. There are even other ways to interpret dimensional contraction in the case of special relativity. It all has to do with how the light, because light is the fastest way that we can communicate in the universe as far as we know. And when we talk about the dimensional contraction of an object as it whizzes past you, you could reinterpret that not as an actual physical contraction, but as the fact that the light coming from different parts of that object reaches your eye such that it appears that the dimension is contracting, but not that it does in reality.
No, it's just the opposite. Penrose showed that you don't actually see length contraction. The object is contracted, but for reasons like you just said, the way that light comes off different sides of it, it doesn't look contracted. The optical distortion exactly cancels out for the special relativistic distortion.
Well,
and then you say, oh, but then why are we even positing it at all? But then you look at like particle physics and stuff.
The reason we're positing it is because mathematically it's appealing to us. But if this is what's actually taking place physically, it's questionable.
I mean, what do you mean? Like, or you think about late 19th, early 20th century physics, nobody was like, oh yeah, special relativity is so much simpler than like what we had before. Everyone wanted to interpret it in terms of a contraction of the ether. Like,
but physics is not a popularity contest. If it were, we would still believe the phlogiston theory of heat, which 110 of physicists believed
Oh, but that's my
300
point.
years
It's like
ago.
relativity was not popular. Like at the
Well,
beginning.
no, and I'm not saying that special relativity's got to be thrown out. What I'm saying is that there are different ways to interpret it.
Yeah, and I'm saying the thing that you mentioned is not quite, I think you got it backwards. Like, you know what I mean? It's like in the 20s and 30s, like you can find books where they will be like, yeah, like if you could see, you know, the guy going really fast, you know, it's like he would be like contracted in the direction.
Well, you couldn't see that guy going fast. If he's going that fast, you wouldn't be able to see it anyway. But
well, when the light, you know, coming off would hit your eye and stuff. But then, yeah, in the 40s and 50s, Penrose showed that you wouldn't actually see the contraction effect because of the one time I like went through the geometrical argument. I understood it for a second, you know, just like, because, you know, the light, you know, off the front of it comes at a different time.
But Matt, the point is you wouldn't see it anyway because the object's moving too fast. It'd be moving too fast for a human being to see it. So this whole thing,
see it. Like, I
and
really,
with Penrose, you know, I have a lot of respect for Penrose. I have a lot of respect for Penrose, but some of the things he's proposed are very outlandish.
Okay, maybe so, but like everyone agrees with this Penrose thing, and I get it, it's not popularity.
Well, everyone. I'm just saying. Like I said, if everyone, we would still believe in the phlogiston theory of heat because everyone believed in it 300 years ago. Like I said, science is not a popularity contest. It's a search for the truth.
I'm saying the larger question is, are there ways of thinking about special relativity that don't involve length contraction? And, you know, there's lots of good reasons for thinking, you know, like, is like, you know, the symmetry, like Lorentz symmetry, is it like necessarily exactly true? I mean, I think there are open questions about that.
Well, look, I have a rebuttal for my own contention, and I think you were alluding to it when you started to talk about particle physics. When certain components of so-called cosmic radiation hit the Earth, there apparently is a time dilation in the decay of these particles.
Mm-hmm.
Because of their speed. So time dilation has been shown to be a real thing. But dimensional contraction is a whole other thing that can be explained in other ways. I don't know, but I'm just saying I have a rebuttal from my own contention that special relativity could all be in the mind of the beholder. Because there is real time dilation of cosmic particles before they hit the Earth. They decay.
Yeah, I mean, they
a lot slower than they should.
Like they put like an atomic clock on a plane, right? And like sent it around the Earth a bunch of times, and then it ran slow.
Yeah, well, right. So time dilation is a real empirical, factor, but dimensional contraction. A lot of other ways to explain it. I'm not saying that it's necessarily wrong.
Yeah, I mean, I think that
But I'll tell you, black hole theory, which Moshe worships. This is his god, black hole theory.
Yeah, he really does black holes. I wonder why.
Since he stopped believing in Yahweh, black hole theory is his god. And although he disagrees with Susskind, he actually published a paper with Andre's assistance disproving Susskind's black hole complementarity, which I give him credit for. But that aside, and Susskind, and he wrote to Susskind about it. Susskind, of course, ignored it. But that aside, Moshe is married to black hole thermodynamics, even though the whole basis, I can punch holes in every assumption about black hole thermodynamics, and which shows that there's zero empirical evidence for a black hole being a quantum object. Of course, whenever I bring this up, Moshe mutes me, And Barry's head explodes because Barry is also married to this crap.
Because nobody is ever gonna be like, oh, so we shouldn't try to quantize it.
But the only progress in science is made by the people who challenge the status quo. I don't care if 110% of all the physicists in the universe believe in black hole thermodynamics. It's based on a set of incorrect assumptions.
Well, I think this is,
And I can show you that. I could probably give a lecture on that, but nobody would pay attention, so why bother?
well, I think it's an interesting point, like the way that things become controversial versus mainstream and stuff, right? Because it's like, black holes in the classical case, as you yourself have pointed out, people had such ideas in the 19th century and then in the 20s with the Schwarzschild solution stuff. But
Yeah,
like,
I believe in Laplace's conception of a black hole. Laplace is the one who conceived of them, and he said nothing can escape from a black hole. That's what I believe. Nothing can escape from a black hole. End of story.
Right. But what I'm saying is like people didn't, as far as I know, even really think black holes were real until like the 60s.
Well, right, because there was no empirical evidence.
Yeah, and so it was like, the outsider position was to be like, of course black holes are real, and then the mainstream is like, no, they aren't. And so,
But
and
then to go on and develop all this conjectural theory that
Right.
has no basis in empirical reality is crazy.
But my point is that a lot of the people who, were making that progress were people who came of age at a time when they had to demonstrate that black holes were totally real against people who didn't even think even the classical case existed.
This is called career preservation. Look at all the money that goes, all the charitable money and government financing that goes towards string theory research. And this is a societal problem because it takes those resources, financial and other resources and intellectual resources, away from real physics. When this money goes towards this fantastical physics for which there's no empirical basis, like string theory.
One thing that I think is hilarious that I think you'll appreciate is that whenever I'm leaving Philadelphia to come back to New Jersey, I always passed this school that must have been founded, back in some of the golden days of string theory. I don't know, maybe it was from like the late 90s or something. And it's like an elementary school or something, but it's literally called like the String Theory School of something or something. Like literally has nothing to do with string theory. But, people it was just the buzzword. Yes.
And string theory theorists actually believe that the graviton has been discovered, because if gravitons don't exist, then their entire careers are over.
Well, I hope for everybody.
But the graviton has not been discovered. I hate to break the news to everybody, if anybody's listening.
I hope for everybody's sake that in the next 10 years, one of the things that comes out of all this quantum, computational engineering is we get a fucking black hole in the lab, and then we can, start figuring out who's right and who's wrong. I completely, like, that is to me the goal. Like, you know what I mean? Like, yeah, maybe we can do it. We're going so fast with the quantum computers. Maybe.
Okay, but the problem with the black hole in the lab, according to black hole theory, it evaporates inversely to its size. So a black hole in the lab would disappear in an instant. You need a supermassive black hole for it to be around for any length of time.
I mean,
so I don't know what we're looking for. Maybe we can simulate something in hydrodynamics that represents what a black hole would do, but still, it's just theory.
I mean, it might have a short life, but I mean, this is just a question of, can you do your experiment quickly?
Well, it would have such a short life that
these experiments on these short-lived, like subatomic particles. I mean.
See, and yeah, but a black hole that you could fit in your hand would have a much shorter life by orders of magnitude than any of these particles that are short-lived.
Is that true?
But let me tell you something. The problem in physics today is that, and also in among the general the ignorant public and government officials who are persuaded by all this nonsense, The problem is that these physicists whose careers are based on all this conjectural bullshit know that their theories can be neither proven nor disproven, certainly not in their lifetime, but probably never. So they're safe in promulgating this crap. Do you know Brian Greene at Columbia University? He's the most powerful physics chairman at Columbia, gets all the funding. Can any of his theories ever be proven or disproven? Of course not. And he goes on TV. His wife, he goes on TV.
Go the Large Hadron Collider. I mean, and you get a disproof. So that's progress. I mean, I don't.
A disproof of what? You know, there was. You know, they try to shut down the Large Hadron Collider before it started up. The local people in Grenoble, because they were afraid that because some physicist said, "Oh, we could produce black holes with this large." So of course the local people said, "What? You're going to produce black holes? It's going to destroy the Earth." There was actually a court challenge to, you know, prevent the LHC from opening, but of course it was, you know, dismissed. And they never produced a black hole in the lab or at any collider, and for the foreseeable future they will not, if ever.
Well, I think that best case scenario for me is like next year or two, we get some like big ass quantum computers.
Again, a simulation, a model, not reality.
I know, but like what I'm saying is like the quantum computers get good, and what we start being able to do is use them to manipulate, you know, matter, you know, condensed matter systems in like incredibly quantum coherent, sensitive ways. So that like there's a synergy, like not just like, oh, we can model a lot of molecules and do drug discovery, or we can do this or that, but literally like you can build sort of like apparatuses that actually manipulate quantum systems that are themselves composed of, you know, thousands, if not millions of qubits. And that increased control will allow us to, you know, go down this road of like trying to make,
you know, don't get me wrong. I'm not denying quantum physics or any of the aspects of quantum physics. I believe in entanglement. In fact, Bohmian mechanics has an essential part of it is entanglement. I believe quantum physics. But what I'm saying is that when you model something on a computer, it's a model.
I agree.
It's not reality.
Not to use the quantum computer to simulate it, but to use it as an instrument.
How is that going to prove black hole theory?
No, I'm saying to use the power of these quantum computers, right? Because if you think about it, it's like, yeah, there's the quantum computer where you're like doing quantum computation, but like imagine like a quantum computer that has like a quantum interface to other stuff. Like, you know what I'm saying? And it's like, you could engage in like finely tuned coherent interactions with quantum systems and then kind of maybe try to grow a black hole that way. Like, you see what I'm saying? Where it's like, it wouldn't be a simulation. It would be like right now, it's like when we manipulate matter, I mean, it's like we're doing it in ever more fine grained and quantum coherent ways, but still it's like not quite at the scale, but you know, the kind of instruments we could create. Like
okay, but specifically in black hole theory, we are eons, we are lifetimes away from producing a black hole that would survive for any appreciable length of time.
That's my contention.
You know,
the rapid increase of quantum computing power will like rapidly, in a surprising way, make it possible. Like that's my prediction.
Well, to do a fictitious model, or to do a fictitious calculation, but to actually create a real black hole in physical space, we're like eons away. You know, it ain't gonna happen.
I feel like it'll
not in your lifetime.
I feel like when it happens, it'll be like, wow, that was way sooner than I thought.
And why would anybody want to create a black hole anyway?
Like you talk to quantum computing people from back in the day, and like, you know, like Scott Aronson or whatever, coming up in like the early 2000s and other people. I mean, like they're still shocked that we even have the quantum computers that we have today. Like they think it's like early. And I think a similar thing will happen, that there'll be a kind of
But we haven't done anything on a known quantum computer. And the most advanced quantum computers that we know are the IBM and the Google computers. We don't know what state actors have. The Department of Defense or the Chinese government might have very advanced quantum computers, but they're not talking about it. But the quantum computers that we have to date cannot perform a calculation any more advanced than a digital computer. Yeah, I know. They talk about quantum supremacy. That what is it? The Google computer and the IBM computer have quantum supremacy. That's been questioned,
Yeah,
by
they're
the
on
way.
track. I mean, the number of qubits is just increasing.
Yeah, right. And like I said, there could be state actors who have more advanced quantum computers, but we probably won't find out about them until the Chinese hackers clean out all of our bank accounts, and then we do something about it. Because that's the way we react as a society. We're reactive. Instead of taking the precautions we should be taking, because the RSA code, you know what the RSA code is? The RSA code will be broken by Shor's algorithm on a more advanced quantum computer. And what precautions are being taken? They're talking about investing in Bitcoin. The banks are going to invest in Bitcoin, so when the next crash comes, the taxpayers can bail out Bank of New York. Bank of New York was just given the go-ahead by the New York Federal Reserve to invest in Bitcoin. Are you kidding me? What about Holland tulips? At least you can smell them. You can't smell Bitcoins. This is one of the worst speculations in human history. And,
I'm actually with you on this.
And what are we going to do? We're going to bail out all these banks who speculated in Bitcoin when the crash comes? This is a last suckers game, like every other crazy speculation in human history.
Yeah.
But that's a whole nother meetup.
Yeah, I gotta go get some dinner.
I gotta go too. Thanks for the talk.
Yeah.
So you're gonna be back next week?
Yeah, hopefully, yes.
Because I need somebody I can harass. People on the street don't want to be bothered.
Yeah.
I have a good one, Matt. Thanks a lot.